So maybe perhaps to connect with what Bertrand said. So there are many ways to define conformal field series. So you may start from the path integral. And then you may try to do that starting from the Hilbert space picture. Together with the symmetry algebra. And you also have the conformal bootstrap axiom that Bertrand was about to discuss. And in my talk, so in my talk, it will be about a specific model where actually you can start from the path integral. And then you can use it, this path integral, to connect with a definition of CFT that Segal proposed in the 80s. And starting from this Segal picture, so you use the path integral to construct this, to show that this Segal axiom holds. And then you can recover the Hilbert space picture and the conformal bootstrap axiom, and also construct the conformal blocks. So this is what I'm going to present with Guillaume in the context of one specific model, that is the Liouville CFT. Okay, so here it will be the Virasoro algebra acting on the Hilbert space. Well, there is a twist compared to what Bertrand said. There is no current here. There is only the Virasoro algebra. So, well, this is more or less the plan of the lecture. So I will explain first what are the Segal axioms in general, how they can be translated into concrete words in the context of Liouville, and then I will prepare with Guillaume the plan to basically have this picture in mind. So you want to connect all the aspects, all these aspects here. So let me start with the Segal axiom. So as I said, it was, well, the paper is in the 80s, in the first year of this millennium by Segal, but it started in the 80s. And it's not clear that, well, it's constraining, as Bertrand said, and it was not clear that many non-trivial examples could fit the definition. That's what Segal said in his introduction. But actually, so in the context of the Liouville CFT, it's really something well adapted, and I will explain first how it goes. So in Segal axioms, you define, you will attach to each surface with boundary components. So it's a Riemann surface, a 2D surface with boundary components, and you will attach to each of these surfaces a probabilistic object. For me, at least a probabilistic object. So in this picture, so you have many boundary components here. They are parametrized. So parametrized means that you have a map, a holomorphic map, from the circle to each boundary component. So one for each boundary component. And so on this surface, you have an orientation. And this orientation on the surface gives you an orientation of each boundary component. And there is one important aspect in this setup is that when you take the parametrization here, it may or may not agree with the orientation given by the surface. If it does not, we call it in component, and if it does, we call it out. So there are two types of boundary components, in and out. And this is what we will focus on. Sorry. So what are the Segal axioms? So you have this boundary components and this surface in between. And basically a CFT for Segal is a map that attaches to each such surface with eventually marked points. So you have this picture. So eventually you have something like that. There might be some holes in between. So you have the in components on the left, out on the right. All of them are parameterized, and you eventually have mark points at location xi and with a weight alpha I. I will so the xi and the alpha I are more or less what the same object as Bertrand described this morning. I will give them concrete meaning in a moment, but in general, the alpha i's well, they parameterize the observables that you want to compute in your CFT, and they can be general here at this level. And so for each such surface, you want to attach an Hilbert-Schmidt operator, and in a way that it's an Hilbert-Schmidt operator that acts on the tensor product of an Hilbert space, and you split the in and out boundary components. But at each boundary component, you attach the same copy of the same Hilbert space. Okay, so this correspondence, it has to obey something that is very important. Is that here, of course, you can glue some surfaces. So if you have a boundary surface like that, you may have another surface like this. Here and out here.
Sorry? Yes. Could you say what M and mu0 are?
So here, this is a generic Hilbert space. I take it to be an L2 space. But for instance, it can be, well, depending on the context, you have to tell us what is the Hilbert space.
It's not something that's constructed from your surface?
No, it's not something that is, it's model dependent.
But who is M and mu naught?
Sorry?
What is M and mu naught?
Any measurable space. Okay, for instance, it's a data. Okay, it's an input that you have to give to check that the Segal axiom are valid. So if you want to define the CFT, you have to tell me what is the Hilbert space and what is this correspondence. Okay. In general, you have to do this. This is your exercise when you want to define the CFT. So there is no generic M working for all.
But for Liouville, you will give an example.
Yes, for Liouville, then for Liouville, my exercise will be to give you what is the L2 of M and mu0, and what is this map that sends a Riemann surface to an Hilbert-Schmidt operator.
Maybe going ahead, but for example, for Liouville, what would be the M and mu naught? Or it is too complicated?
Okay, so in general, I will say a word about that, but in general, what will be this Hilbert space? You will have a random field defined on your surface. You will restrict this random field to a circle, and then so your random field will take value in some space. Here it is, E. And so typically this space is the space of maps from the circle to E. That's the more reasonable choice you can take, and that's what I will do actually. Okay, so. Here, you may glue your surface analytically here with the out and the in component together. Why? Because you want to preserve the orientation at the gluing. And so this gives you this surface here. Okay, so there is a natural way to glue the surfaces on boundary components. And so this map has to respect the gluing in the sense that if you glue two surfaces together, the operator, the Hilbert-Schmidt operator that you've got here, have to compose. So you have an operator here, an operator, Hilbert-Schmidt operator here, and basically the amplitude, the Hilbert-Schmidt operator that you have on the surface is the composition here of the two. Okay, this is the idea. Okay, so let me, and of course what's important is that if you have no boundary component, so if the surface is closed, what you should get as this operator is the correlation function you want to compute. Okay?
But for cylinder, do you have projection property? Or it is not TQFT, right? So what do you associate to a cylinder just?
For a cylinder, you have to associate an operator. What is your?
If you compose it with itself, so it should reproduce itself in some sense.
It will be a semi-group. We will focus on the cylinder situation, but what is very nice with cylinders is that it gives you a semi. Because here, it's not topological, so here the conformal structure matters, but still it will give you a semi-group.
They have mark points also.
So as I said, so what is really important for Segal is that, as I said, well, if you glue two surfaces like this, you get a Riemann surface like this. This is what I drew, and the amplitude, they have to respect the gluing in the sense that the amplitude of the glued surface corresponds to the composition of the operators. Well, there is a caveat, of course, according to the components you have glued together. Okay, so you have to express this in a complicated way with a trace. The trace just means that you compose the operators along the boundary, the components that you glued. Okay? Is that clear?
So this setup does not really know about conformal boundary conditions, or at least not yet.
What do you mean by conformal?
You told us that correlation functions would only be when you have a closed surface.
You mean when you compute correlation functions for open surfaces?
Yes.
Okay, so I will talk about that at the end of my talk.
Okay.
I will extend the setup, but the problem with the open surfaces is that concerning notations, it's a bit easier. So I will just give you the picture for closed surfaces, and then I will explain again the philosophy for open surfaces. Okay, so you have a couple of more geometric rules to obey if you want to be a CFT at least. So you have to respect diffeomorphism in the sense that you take a diffeomorphism of your surface, and the amplitude, they have to be invariant under, so these operators, they have to be invariant under diffeomorphism. It means that if you map sigma to psi of sigma with a diffeomorphism, the amplitude are the same. Okay? Up to the fact that, of course, you push the metric with the diffeomorphism, and you push the points according to the diffeomorphism. Okay? So this is well, this is just invariance under parametrization. This is natural for actually for any QFT, not only CFT. And what is specific to conformal field theory is that you have to obey a rule according to the scale of the metric. So if you have a G, a Riemannian metric on your manifold, and you scale it with a conformal factor, so exponential of omega, the operator have to be related by a very simple rule. So this is general for any CFT. So first, you see here that there is a factor involving the conformal factor. And in front of them, you have some weights that are usually complex. These numbers, delta alpha I, are called the conformal weights of your operators. And then here you have a global factor, which is completely geometric. Here, kg is the curvature on your manifold. So you integrate the curvature and the gradient square, the conformal factor on your manifold. And this is it's called the Liouville functional. And you have a factor in front of it, which is just the number, complex number eventually, which is called the central charge. Okay, so this is a geometric rule that tells you how your operator reacts when you change the metric. Okay. So either by a scale or by a diffeomorphism. Any questions? Okay, so now how do you implement this for the Liouville CFT? So let me start with the description of the object you want to construct. So basically, Liouville CFT, to start with, it's a path integral on closed surfaces. I will explain later the link with the amplitude. So you want to construct a formal integration measure. Okay, so this functional integral runs over some space of maps. So here it's just a space of maps that are defined on the manifold with value into the real line. And formally, this guy here is just the uniform measure, Lebesgue measure, if you want, on all of the maps of this form. Okay, so it's just a formal object. You have to understand it as the Lebesgue measure, but you want to weight the Lebesgue measure by this functional, which is the Liouville action. So what do you have inside? You have the exterior derivative squared. Exterior derivative. Here, this is the curvature. So all of this, it's quadratic, so basically it means that this part is just given by the GFF, if you want. But here you have a nonlinear term, which is the exponential of the field. Okay. So this makes the difference between the GFF and the Liouville theory. Okay, with this nonlinear potential, you have basically three parameters, but actually the Q here is just can be expressed in terms of the first parameter gamma, and mu is just a scale. So the theory is invariant under scaling. Okay, so basically, you have to. There is only one parameter. This is gamma. Okay. And here, so the vertex operators are just exponential weights of the field. Okay, so you can think of them as a Laplace transform if you want. And if you have a measure, the measure is characterized by the Laplace exponent. Okay, well, this is basically the framework. So if and the correlation function are the expectation values of these guys, provided that you can define this measure, this measure on some space, measurable space. If you can define this measure, you just plug these guys as a test function inside this measure, and you want to compute this expectation values.
Sorry, is this Q related to the Q in the previous lecture?
Yes.
So you never want Q to be 0, is that right?
In my case, it's never going to be 0. Actually, it's always bigger than 2 in my case.
Okay.
It can be negative either.
Yeah, if you want to make it negative, you change gamma to minus gamma, but the theory is invariant under gamma becomes minus gamma. So we can just focus on the 0, 2, and the Q can be negative, but the central charge is still bigger than 25 in all cases. Okay, so
at an abstract level, I mean, is there any normalization of the formal path integral you write there?
what?
The normalization, 1 over.
No, it's unnormalized.
Really unnormalized.
It's not it won't be a probability measure. It will be a measure, and actually it's important to unnormalize. Well, it depends what is your normalization, but it's standard to have unnormalized measure here. So to that the correlation function here match the literature, but you can divide by a constant if you want, and that won't change anything.
And the central charge is related to gamma? Is it?
Well, okay, it's a good question. So, yes, the central charge, okay, I think the central charge is in gamma because if you just plug the formula, it gives you this. Okay, so of course it's analytic. 6. Sorry. The point is that what we do, we cannot prove that our construction is analytic in gamma. Actually, we can, the blocks, you can expect them to be analytic in gamma. I will talk about the structure constants. We can show for sure that they are analytic in gamma. But then there is an integral of all of this. And we don't know if our correlation functions are analytic in gamma. So it means that we are really constructing the Liouville theory on the real line. And we don't know how to extend it analytically in the complex plane.
You expect something?
Something. For sure, I expect something. Sylvain will tell you, of course, it's analytic and you can define a theory, but then if you want to prove a math theorem, it's a mess.
So in particular, gamma pure imaginary, you don't have any idea.
For the non-compact Liouville theory, with imaginary.
Exponential becomes compact.
So okay, depends on the model, because what is important here is the space you want to describe. So if you tell me, take a gamma imaginary, for instance, but I take, if I can choose the space of maps, so for instance, I would change the space, because you have a symmetry, if it's imaginary. So if you impose the fields to be taking values in the circle, then I can construct a CFT with this potential, but we call it the compact case because there is also a non-compact Liouville theory, imaginary. And in the non-compact case, it's not clear mathematically. We have some ideas, but it's not constructed yet. Well, in the case where you take maps taking values into the circle, you can construct a CFT with which is not a GFF, but with a central charge that is less than -1. Okay, so let me now let me explain with a few slides the philosophy for the Segal axiom. So basically, Segal had in mind the path integral, and the connection is not clear with the axiom I gave you, but he had in mind the path integral, and this is this philosophy I want to explain, and how we can twist it a little bit to make it work for Liouville. Okay, so if you have a path integral, what Segal had in mind, but it's a general philosophy. Here I stick to my notation for the Liouville case, but Segal wants to do the following. If you have a path integral, you can certainly construct it on Riemann surfaces with boundary as well, by just, if you just constrain your path integral to take prescribed boundary values. So just an unwavering argument. Imagine that you can integrate over those phi, which have prescribed boundary values, then this definition here will certainly give you what should be an amplitude. Okay. And as I told you, the Hilbert space would be then, naturally, some L2 space of maps defined on the circle, taking values into, in my case, the real line, but for any CFT, whatever the space, so you would have, I call them phi, you would have maps defined on the circle taking values into E. E is any Banach space where your random field is supposed to live in. And basically, you should have some kind of, this is some kind of Sobolev space on the circle. And then you have to plug a measure that is, the mu0 here would be the Lebesgue measure on those maps. Here.
Please, S1.
Yes, this is the circle. This guy is just the circle.
No, but it's S1.
Ah, yes, S1. Okay, so maybe I will confuse S1 and T in my talk. Okay, so that would be the natural definition you would give actually for any path integral, as long as you have a Lagrangian description, meaning an action for a guess for the path integral.
So your Hilbert space is not separable in particular. Your Hilbert space is not separable.
This one, well, okay, for now, I'm not talking about separability because I told you here that this is the Lebesgue measure, but I have no idea as a mathematician what is the Lebesgue measure on this space. So I wouldn't speculate about it being separable or not for now.
And why this Sobolev space is important?
because I wanted to give you something concrete, but Sobolev is not that important. Just this is just trigonometric series. If it's defined on the circle, it's certainly a trigonometric series. And then for now, I will give you concretely the definition in a moment, but for now it's just a speculation. This is what Segal had in mind. And okay, so why would the gluing be true? So just because of the conditioning, so imagine you have two surfaces, well, or at least a surface that you can cut. So let me give you an example. So you have this surface here, and you want to cut it with a curve, an analytic curve. You have sigma 1 here, sigma 1, 2, and the glue surface is sigma that you glue with sigma 2 along this cut. So assume that the action is local. Action is local means that it can be split this way, where your action is just on each surface, just the restriction of your action on the given surface. Okay, so the path integral for this closed surface would be to take any equation function. So you have some marked points here, some marked points here, eventually, and you have your action. Okay. So formally, this is an integration over all those maps. What you may want to do is to condition the restriction of phi along this curve. Okay, so phi. Restricted to the curve, I call it C. Okay, so I condition here on the restriction of the random field to the curve. And so as this guy splits this way, I can split this guy here. So I would have S minus S sigma 1. But since I condition on these values, here I would have that phi restricted to the curve CS is equal to phi times the same type of things on sigma 2. And here again, the restriction to the curve is given by phi, and I would integrate this along G phi. Okay?
You forgot the V alpha.
Ah, yes. And here you plug all the V alpha. Okay, that belongs to sigma 1, and here the same, but you just put the sigma, the xi that belongs to here that belongs to sigma 1 and here to sigma 2. Okay? And here you can see that these two guys, they are just the amplitude that you get. So this is the amplitude on sigma 1 with the xi in sigma 1 and G 5. The amplitude on sigma 2 for the xi that you have in sigma 2. This is a function of phi. And then you see that you integrate with respect to this Lebesgue measure on the restrictions. Okay? And if this guy is, if this integration measure is your Hilbert space, this is just, I will shortcut the notation like this. In your Hilbert space, okay? So if the action is local, what we guess should fit the bill. Well, the problem is that my Hilbert space is ill-defined because of the Lebesgue measure on the space of maps, okay? So let's see how we can arrange this. Well, what's nice is that if we want to define the amplitude this way, it can be, well, you can, to encode this, this boundary parameterization. So if I want to define the path integral with the maps restricted to the boundary components being given by some arbitrary function phi I, I can certainly do this by splitting my field phi into two components. One is the harmonic extension of the boundary values. And then just phi 0 is just the maps that vanish on the boundary. And why it's interesting to do this? Because of the GFF, actually, when you take the gradient squared and you apply this gradient squared to the sum, it's split as a sum of two gradients. Because the harmonic extension is orthogonal to any gradient. So you have a description this way. And here, this path integral, we know how to formulate it because we are integrating the square, the gradient square, on the space of maps that vanish on the boundary. So here I have a probabilistic description in terms of an object called a GFF. The harmonic extension is not something hard to define because just if you give me any surface with prescribed boundary values, I can harmonically extend it. The problem, if you do so, as I said, is that your measure on your Hilbert space, on this space of maps defined on the circle, is the Lebesgue measure. And you know that there is no such guy mathematically, and because you are on an infinite dimensional space. And so when you are in infinite dimension, what you can construct as a measure is a Gaussian measure, right? So you just have to change the measure here to make it Gaussian. Why? Because if it's a Gaussian, I know how to define it. Okay. So you change the measure. And but what is important if I change the measure is that it does not depend on the surface. Okay? The Hilbert space does not see the surface. It has to be a Gaussian measure defined intrinsically. So what I want to do is the following. If I have a function defined on the circle, if the space is nice there, I can certainly analytically continue the trigonometric series inside the circle. I call the PD this harmonic extension, and then I take the gradient squared. Here it will give me a Gaussian measure. But if I change the measure this way, I have to change the amplitude accordingly, okay, to absorb this change. Okay? So I have to plug this guy in the definition of the amplitude. So actually, one question you may ask from scratch is that, well, you can put everything as a red factor here, you can put everything that you please. You could put everything here. The problem here is to have a well-defined operator. Okay? I could put any quantity here, I would have to compensate here at this level. And well, it could be a definition. The problem is that you have to define this guy here, and it has to be a nice operator, okay? And so why is this guy a nice operator? It's because of the behavior of this harmonic extension close to the boundary components. If you have a surface like this, if you have an harmonic extension in the surface locally close to the boundary, it will just behave like the harmonic extension inside the disk, locally close to the boundary. Okay? So basically, these two guys, when you are close to the boundary, it's a super smooth operator. It's a smoothing operator. Okay? So you can take any arbitrary choice here, but then not all of your choices will give you something nice here. Okay? So what I do is that I just make the measure Gaussian in a way that it's very close to what you expect as the behavior of this guy close to the boundary components. Okay? And so now you're here, you're in good shape because you can define all of this. Okay? And this is what I will explain. Now, so this was just the philosophy. And not concretely, this is the definition of my Hilbert space. So I take the space of maps defined on the circle and taking values in the real line. And I want to equip this space with this Gaussian measure. Okay, what does that mean concretely? It means that any map on the circle, you can expand it as power series, just the Fourier coefficients. The Fourier coefficients are this phi n, and the map is real. And I can, if I want, I can just reparameterize all my coefficients in this way. And this measure, expressed in these coordinates, means that the xn and the yn are just independent standard Gaussian. Okay. So this is what I want here. This is just the standard Gaussian. And your random field on the circle is just that you sampled independent Gaussian, xn and yn. You form the trigonometric series here, and you get some random element. You have to be careful here. You have to be careful about the mode 0, in the integral of the field. Because here, if you take a constant field, the harmonic extension is constant, and so the gradient is 0. Okay. If you just project this measure on the constant function, it should be the Lebesgue measure. Okay. So there is just a twist, is that the 0 mode is sampled according to the Lebesgue measure. This is the Lebesgue measure. Okay. So it's not really a probability measure because of this guy, that is an infinite measure. But the non-trivial components of the modes are just sampled according to Gaussians. Okay. So this is my Hilbert space.
But what is the convergence condition of the series? So your Fourier series should be convergent, which makes...
Okay, a good question. I forgot to mention here. So here you just have a measure. I didn't tell you where this, in which space this measure lives. Actually, you can show that this measure it lives. So I mentioned the Sobolev spaces, so you can show that this measure lives in H minus S for any S positive. So the support of this measure is the trigonometric series that are in the Sobolev spaces of negative index. So there are really distributions. Okay, so this is the Hilbert space. And now, how do you define the amplitudes? So as I said, there is a probabilistic interpretation of integrating the square. This is the first statement. So as a path integral, this is if you see, look at formally at this path integral, so you have a field that has prescribed boundary condition, and you want to weight the Lebesgue measure according to the Dirichlet energy. This is a well-known probabilistic object. It's called the GFF, the Dirichlet GFF. And so it can be really expressed in terms of a probabilistic object. So here you have what is the determinant of the Laplacian, that is the normalization, natural normalization of your measure. So this is the mass of this measure, and then if you formally divide by the mass, you get a probability measure, and it's just expectation values with respect to the GFF. You have to be careful that here my expectation as an index, which is phi. Phi here is prescribed, so this is not random. Phi is just boundary, prescribed boundary values. It's not random, it's deterministic. The only guy that you integrate over here is the GFF, X. Okay? Okay, and so what is the definition of my amplitude? So you have this A0 that we call free amplitude. So what do they capture? They capture this constant here, I plug it here. You have the difference of the two harmonic extensions that I mentioned before. And then you are just left with computing these expectation values, where the field of phi here is just split as a sum of the Dirichlet GFF plus harmonic extension. And so if you are familiar with the GFF, I won't spend too much time on it, but what is really, if you have a Gaussian measure, you can certainly perturb it with a linear term. That's not too bad. So it's just a shift in the GFF, but I won't expand too much. This guy is not a problem, it's a linear perturbation. What is really important is this guy here, the red term here. Okay, because the GFF, it's this xg, it takes value also in a negative Sobolev space on the surface. So it's not a random function, it's a random distribution, but it's not smooth enough to be seen as a function. And so exponentiating this guy is not something obvious. But this is something that you can do probabilistically. This is what Karen did in the 80s. So how do you do this? You take your GFF. So as it is an irregular function, the first thing you may want to do is to say, well, okay, it's not smooth enough, but I can certainly regularize it a bit with a modification, say. Okay, I call this modification xg epsilon. The convolution with the modifier, whatever. And then, well, under some normalization for the scale, this guy, if you just look at this guy, it diverges. But it diverges in a way that is completely trivial because it's given by the expectation of this guy. So if you remove the expectation of this guy, you get an object, and if gamma is small enough, so this object, it always admits a limit. The problem is that, is the limit trivial or not? And Karen showed that for gamma small enough, so this is where you see the condition gamma. For gamma between 0 and 2, this guy converges, it's called a GMC. And it gives you a well-defined object, a well-defined random measure that is non-trivial on the surface. And so, here you have the volume measure on the surface, and so you can make sense of the total mass of this measure on the manifold, which is the integral over sigma of the exponential of the field. This is a random variable, and you can compute. It's a random variable. It's positive, and so you can certainly compute this expectation value on top, and it gives you a definition for this amplitude. Okay, so I will be a bit fast here if you're not familiar with GMC. I know that some of you are familiar with that. But the message here, and it won't be, yes?
So maybe naive question. So gamma is epsilon independent. So what is the point of keeping it in the limit?
Gamma is certainly epsilon independent. What is the point? Keeping what?
In keeping in the limit. So why you cannot take it out of the limit?
The what, the gamma?
Because limit is over epsilon, so gamma is epsilon independent. So I don't.
It's the metric G. Maybe it's.
I'm not sure. You want to skip gamma?
Yeah. What is the point of keeping this coefficient, which is constant, right? So the gamma.
Epsilon to something.
It's epsilon raised to the power.
It's epsilon to
The limiting object depends on gamma.
Yeah, but it doesn't depend on epsilon, and your limit is over epsilon.
The first factor is epsilon to the power gamma square. It's not exponential gamma square. Is it?
So there is a.
It's not.
This is epsilon. Yes.
Epsilon.
This guy is epsilon. Okay. Yeah, it's. This guy diverges. You have to multiply by something going to 0.
Yeah, but there is some epsilon missing. You mean?
The epsilon looks like an E, I think. It's
It's not E, it's epsilon.
because
I also have a hard
it's not exponential of gamma square. It's
Maybe it's because it's written with two ones.
it's E to the power gamma square.
Epsilon. I see.
Okay, the epsilon, this one is not that good.
Can you say a word why this is working? Why does it exist?
Okay, I won't give you the full argument, but what you can do is certainly. Okay. if gamma is even smaller, okay, less than square root of 2, recall that the threshold is optimal is 2. But you can say, okay, I'm not ambitious and I just want to check this one. Then the convergence is in L2. Because this convergence usually is in L1 plus something. But if gamma is small enough, you can compute in L2. And for instance, you can just compute the square of your approximation. Let me call the approximation gamma epsilon. This guy here. If you compute the square, basically you are computing this guy. Of x, y, and there is an epsilon gamma squared in front. But you can then plug the expectation inside. Then you have the exponential of Gaussian. Okay, so this is computation that you can certainly make. This expectation of Gaussian gives you that it's more or less exponential gamma squared green function. The green function is more or less the log. Okay, and okay, so there is at least a range of parameters for which you are in L2. But going beyond L2 is more complicated. Okay, so the theorem is the following. If you accept my construction, so these guys provided that some condition is fulfilled. So here you have the Euler characteristic of the surface. So if the sum of the weights, the sum of the mark points, is bigger than the Euler characteristic times Q, then this amplitude, together with the Hilbert space I give you, they satisfy Segal's actions. Okay, so you have you have a model that obeys all the Segal actions. In particular, they behave well under gluing of surfaces. Okay.
Is it possible to understand why there is this condition?
Yes. Okay, I forgot. Yes, I forgot. There is another condition that I did not insist on. First, the alpha I have to be less than Q. So why? Okay, you have your chaos. I will talk first about the first condition. Alpha I less than Q. This is similar to some geometric theorems. It's just now in the probabilistic setup there is a twist. Okay. If you shift, so how do you make sense of this guy? Because here I told you phi is not a well-defined function, so actually you cannot evaluate this guy at a point. You need to regularize this guy as well. And for Gaussian, it's simple. It's a complete square trick in physics. It's very simple. And in math, it's called the Gersonov theorem. So what is the effect of this Gersonov to complete the square trick? It's just that you can remove this guy up to shifting the field phi here. Okay, so your measure, it's your random measure here, exponential of the free field. But when you shift this guy, it will create basically a singularity which is of this type. Gamma alpha I. Okay? So the question is this singularity integrable with respect to this guy? So if you are in the Euclidean world, you know that this guy has to be less than 2. Okay, to be integrable with respect to the Lebesgue measure. In probability, it's a bit different. This guy here, it's a multifractal random measure. You can still analyze its behavior around the point. And the singularity is the mass of the balls. When you prescribe the ball, the balls stay like this. So to be integrable, you have to have gamma alpha I, the singularity less than gamma Q. Okay. So it gives you the first condition. For the second condition,
alpha less than Q or more than Q?
Less than Q. The singularity shouldn't be too strong, so it has to be less than something, and the something is here.
But can you comment on this? So I think you're making points that if you want to integrate one divided by absolute value of x to alpha, then it has some problem at zero. But you can analytically continue this as a function of alpha, and then you have no problem anyway, except that you have poles. So
You want to analytically continue in
Yes.
alpha? Yes, we can. But that's. But why do you say that you have no problem?
Huh?
Why do you say that you?
because as a function, absolute value of x raised to power alpha as a generalized function is continued analytically with respect to alpha. So the fact that it's divergent, you can canonically regularize it. So why do you?
Well, here you have to define a random variable in the end, so you have to integrate over the surface. Okay, this random variable, you can certainly analytically continue it in alpha, and you can even analytically continue it in gamma. What is not clear is that you can, because then you have an expectation value with exponential of minus the guy. What is not clear is that this almost surely the random variable is analytic, but it's way harder to show that the expectation of the exponential moments are analytic, and that we cannot do it. Okay, one reason for this, say, okay, let me give a waving argument. You want to focus on what happens to the field, okay, on what happens to this guy when the field takes large values. Okay, there are two ways of taking large values, super high values or super negatively large. For negatively large, for super large, positive large values, this exponential here will kill everybody. But then you see that this guy, when phi is super negative, won't contribute to anything. So you have to gain something from the alpha I here. Okay? And so you have to get the alpha I large enough to make this guy goes to zero when the field is super negative large. So it involves certainly the sum of the alpha I, but then you have contribution from the Gauss-Bonnet theorem here, and this gives you this condition here. Okay? Okay, so
this condition is to make the A to be in L2, but you could still define something.
This condition makes you.
It's to be in L2 to be Hilbert-Schmidt. If you
mean the kernel L2?
Yeah, the A will be an L2 function of phi, of the blue phi.
Then you have way more than L2 here. It's simply bigger.
Yeah, but this implies that this is in L2.
Ah, yeah, this is in L2. You mean that?
But if you don't have this, you could still define A which is not in L2.
Yeah, okay, this condition is to make it Hilbert-Schmidt. Of course, you can define this guy as long as you have a boundary, even if it's not Hilbert-Schmidt for values that don't obey this condition. But then it's later. Any more questions? Okay, so this finishes my part on the Segal axioms. And now I want to talk about something that will be important to define the blocks, and that is important usually in CFT, the structure constant. So you may focus on the 3-point correlation function on the Riemann sphere. So why are these guys important? You will see later. This is related to point decomposition of Riemann surfaces. But for now, I will just explain what is this guy. So you are on the Riemann sphere. Your surface is just the balloon. And you want to compute these correlation functions. So why 3, why not 2, why not 1? remember that you have a condition. So here, the surface S2, it has no boundary. So to have a well-defined correlation function, at least according to the last condition I gave you here, this one, if you adapt it to the case of the sphere, it tells you that the sum of the alpha I has to be bigger than 2q. Okay? But also the alpha I have to be less than q. Okay, and if you combine the two, it tells you that the number of points that you on the sphere, you need at least 3 points. To have well-defined correlation functions. Okay? You can have more, but at least you need 3. And for now, I will be just interested in the minimal number of points I can take on the Riemann sphere. So you want to compute this quantity here. So now you can use the symmetries to remove a lot of guys. Actually, first I fix the metric, and the metric I take it to be the round metric on the Riemann sphere. And why can I do this? Is because on the Riemann sphere, every metric is conformal to the round metric. So I can use the diffeomorphism invariance and the scale invariance to reduce, to this case, up to trivial factors. Okay? Also, actually, there is something important, is that the automorphism of the Riemann sphere are the Möbius transformation. And because of the two axioms I mentioned, the dependence, if I apply a Möbius transformation to this correlation function, I can use as well the diffeomorphism invariance and the scale invariance to have a completely explicit dependence on the localization of the points. Okay? So it's completely explicit expression, and so up to applying Möbius transformation, I can reduce to this quantity here. Okay. 0, 1, and infinity. And so there is a theorem that won't be the focus of my talk, but what the message is that in our case, it's completely explicit. The 3-point function for the Liouville theory on the Riemann sphere, they are given by a DOZZ formula. So it was given in the 90s by Dorn, Otto, and Zamolodchikov. So that's the name. So it's a crazy expression for the 3-point function. So you've got here the Zamolodchikov function, or it's also double bounds in mass. So how do you define this function? You consider this integral. You can show that it's defined for the real part of z between 0 and q, but actually you can extend it on the whole complex plane. It gives you a well-defined function epsilon, and then you have this formula for the 3-point function. So let me be clear, I won't need this formula in my talk. But for one thing is that you can see that it is clearly analytic in all the parameters. That will be important. But for the rest, you can forget this formula. Just to give you an example that the kind of crazy function you can get out of this Liouville CFT. Okay. I think I will stop here because this is the perfect moment to stop. Guillaume will talk tomorrow about a question you asked about the semigroup of annuli. So in this semigroup of annuli, it's very important for us, and it was already mentioned by Segal at the time. We will be able to define 2 objects. First, the Hamiltonian of the theory, and it's a bit like it has a similar importance as the Casimir for Lie algebra or something. It will serve to get an orthonormal basis for our model in the Hilbert space. And so the philosophy for the bootstrap will be to explain as Plancherel formulas some building blocks of the surfaces. So one important output of this semigroup of annuli is first the definition of the Hamiltonian, and then the diagonalization. But then you can have also a semigroup of annuli that is not generated by a straight dilatation, but more complex holomorphic deformations. And then Guillaume will explain tomorrow that how it encodes all the symmetry algebra, so the Virasoro algebra, by deforming annuli. So I think I will stop here for today.
Small recap of yesterday. So we were looking at the surface, Riemannian surface. That's the boundary, and we had this action, which was the Liouville action. And we defined this to be the integral over sigma of the differential of phi squared evaluating g plus q Ricci curvature times phi, and we have this potential phi. So q was a parameter which is equal to gamma over 2 plus 2 over gamma. And gamma is some number in 0, 2. And so maybe, and we wanted to construct a path integral which was with respect to this action. And maybe let's recap a few properties of this thing. So the properties of, so in fact, all the algebraic properties of your measures is going to be encoded in the mu equals 0 case. So let me recall the property of S sigma 0 and the properties of the measure we want to construct. And so, well, here we saw that the S0, when mu equals 0, this is quadratic. And this gives us a Gaussian measure. It is also diff invariant, so if I pull back my metric by diffeomorphism, I get the same action. And this is, of course, the same property that you have for the measure. And it is also it also has a cocycle property, and this gives you the Weil anomaly. And the cocycle property, I'm not sure that Rémi mentioned it in full, but let me write it in the at least 2 equals 2 case. So the cocycle is that if I look at S sigma of phi with phi 1 plus phi 2 in the metric G. This is the same as S sigma of phi 1 in the metric e to the phi 2 G plus S sigma of phi 2 with respect to G. And this means that if I replace phi 1 by my field, which I want to call X, say, and phi is just some smooth guy, then my action is like this. And you see that up to something that is independent of X, I have the same action in this conformal equivalent metric. So this gives you the Weil anomaly. When Q is not equal to 2, you just have some scaling thing. So you have to do some algebra that is easy, but that I will not be able.
You're talking about cocycle.
Yeah, so you would, as I'm telling you, you would have to rescale this guy by Q maybe, or Q over 2. And if I do it on the board, I will make a mistake, so I will not do it. But basically, you have to put Q here, and then you have a Q square in front. And maybe the last property that we want is that this action is local. So meaning that if I cut, say I want to cut my surface along a geodesic, something that is geodesic, so with 0 geodesic curvature here, then I have that the S sigma of the field of the glued surface is the sum of the actions, and this gives you the gluing property. And essentially, when you add this mu, when this mu is not equal to 0, well, you have to do some probabilistic multiplicative chaos to get make sense of this measure. But essentially, all these properties are conserved in the when you add this mu. So all the algebraic properties of the measure are encoded in the mu equals 0 case. And then you have a machinery called GMC, or Gaussian multiplicative chaos, that allows you to make sense of the mu different from 0 case, and all these properties are remain in the path integral.
Sorry, can you remind me what the central charge is in terms of this cube?
Yes, so this
1 plus 6
is
or 13?
Sorry?
Yeah, just what is it?
The central charge is CL, is 1 plus 6q squared, and you can check that this is bigger or equal to 25. And so in particular, as Rémi mentioned, Q is always different from 0 in our case, so we are in a slightly different setting than Bertrand's talk, where Q is equal to 0. And maybe, okay, so to advertise this talk, so this is about, this wide anomaly is about conformal changes of metric, and now basically this talk is going to be about when we change the complex structure. So how does the measure vary? When we vary the complex structure.
So before you go to that, there was a
Sorry?
Before we go to that, there was a whole previous lecture which explained how you deal with exponential. So can you, quickly in 1 minute summarize why you can deal with exponential, although it's...
Yes, so the exponential, so Rémi told you that so when we look at this, measure, so at mu equals 0, we have a Gaussian measure, and the field is going to be, so it's not going to be a function, it's going to be a distribution. So to make sense of the exponential, it's difficult. But what Rémi told you is that you can make sense, so if x is the GFF, you can define m gamma, and measure m gamma of z, which is the limit as epsilon goes to 0 of epsilon gamma square over 2 e to the gamma x epsilon of z, where this guy is now a regularization at scale epsilon. And so you can make sense of this measure. Then the integral over the surface, so almost surely under the GFF measure, this total mass is going to be well defined, and you get an absolutely continuous measure with respect to the GFF.
There is a measure eventually on
Is that alright or?
time as well.
I mean, I can. Okay, this was done this way. Yeah. So now we want to understand how this measure is going to vary when we vary the complex structure. So how would we vary the complex structure? So here we were not varying the complex structure with the Weyl anomaly. We were just taking a conformally equivalent metric. But now I could also apply a quasi-conformal deformation, for example, and I would not get a conformally equivalent metric. But I can still ask how this measure is going to vary. So I can ask how the measure vary when I quasi-conformally vary the metric, and this will give me a variation of the measure. So we have basically a family of measures indexed by the Teichmüller space, if you wish, of your surface. And the question is how this measure varies. And it is a well-known fact, so in a tedious computation, that the variation of the Liouville action of this S sigma 0, this is equal to the stress energy tensor. Which gives you a concrete formulation of what Bertrand was saying, I guess. So, which means that if you vary along some, say, Beltrami differential nu, this is going to be equal to the pairing of the stress tensor with nu, and then the T here is minus bx squared plus q dz x in the local coordinates, say z. And here I put some, then you can check that if you have this sort of a, if you have this sort of expression, it's not going to be, so it looks like a quadratic differential because I have a dz x squared and dz squared, but it does not transform as a quadratic differential. It transforms as what is called a projective connection. So if you change if you do a change of coordinates, this guy is going to transform anomalously t plus CL over 12 times the Schwarzschild derivative of psi, where this S psi, okay, so now there's many S's, but this psi is psi double prime with psi prime and this one. And you get, this is something you can check, and there is so the central charge, there is a 6q squared that comes from this guy, and this needs a renormalization, which gives you actually the Bergman kernel. It's a known fact that the Bergman kernel gives you the one over there. It transforms as a projective connection. Okay, so this is just to advertise what we're going to do, but I'm going to make this a bit more precise. And essentially what I want to do in this talk is to explain how the Biarasso algebra is going to appear from the stress energy tensor. Okay, and this is what we're going to do now through what is this semigroup of annuli and these flower deformations. And I will start here. Okay.
Push the board
Yes.
a bit more though.
Sorry.
In that differential, then is written the u is something like quadratic differential.
So like a Beltrami differential.
Time differential.
The t is so it looks like a quadratic differential even though it's not quite. So you can do there's a natural pairing between quadratic and Beltrami. The product of the two is a 1-1 form, which you can integrate on the surface. Okay, so now let's go to the semigroup of annuli, and the spoiler is that the Biarasso algebra is going to be the generator of an infinite dimensional semigroup, which is the semigroup of annuli. But to warm up, let's look at just a one-parameter semigroup of annuli. So here the parameter is t, and I look at the straight annulus in this lime color. So between so modulus of z between e to the minus t and 1, and the metric is just this flat metric with geodesic boundary. And as Rémi told you yesterday, to have a surface with boundary, you need to have boundary parameterization, and here I just take the trivial parameterization. And you can define an operator, which is the amplitude that Rémi introduced before. And the amplitude was really this measure. It was, well, actually it was really this measure, which was the path integral with respect to this action. But you condition by conditioning on the boundary field. So here you must imagine that you have two fields, one phi here and one phi prime inside, and the amplitude is really the kernel of some operator. So it depends on two fields, the two boundary fields, and you can understand it as the kernel of an operator. So you understand. So this S of t has a kernel, which is just the amplitude that I associate to an annulus. Is that okay? Okay.
This is not the integral over h, it's over h. It's over the solar space of the circle.
Yes. Yes, it's over. Yes, sorry, it's over the solar space. So it's. And so what was proved by Colin, Antti, Rémi, and Vincent Vargas recently is that this is actually a semigroup of operator on the Hilbert space, which has a generator that you can call H. So it's a semigroup of contraction. And you can apply the Hilo-Yoshida theorem to this semigroup. It's a Hamiltonian, which is called the Hamiltonian of Liouville CFT. And so the proof that this is a semigroup is very easy. So if you have two annuli, you can glue them together to get a new annulus, but by the gluing property of Segal, the operator that you associate to the gluing of these two annuli is just the operator associated. So the operator associated to gluing is just the composition of the two operators. So you get a semigroup. You have a one-parameter semigroup of operators acting on your Hilbert space, and you can extract a generator. And this operator is called the Hamiltonian of Liouville. And the interesting thing is that you can generalize this thing. So now what you do is you pick an arbitrary vector field, holomorphic vector field in the unit disk, and you ask that the real part of V of z over z is negative on the unit circle. And this is a geometric condition that tells you that this vector field on the boundary is going to point inwards. And once you have this condition, you can look at the flow. So you're really taking at the exponential of your vector field. And it's going to generate actually a flow ft of conformal maps. And these conformal maps, they are going to shrink the disk. So you do dt ft equals v composed with ft with the initial condition, the identity. And it's going to create a flow of conformal maps that contract like this, and that will eventually shrink to a point. Okay? And this defines for you a geometric annulus with one boundary, which is the unit circle, and the other boundary, which is the curve inside. And you get the parameterization of these two boundaries. What is it? Well, you just take the identity on the unit circle, and on the other boundary, you can take just the parameterization induced by your conformal map. So you have z goes to z on S1, and z goes to ft of z on the other boundary. So in and out.
Is VZ generated by the semigroup, or is it separate from the V? This that you took here, is it generated by the semigroup or different?
So the vector field generates a family of annuli which are in the Segal semigroup of annuli. Okay. And so what is the example? Why does it generalize what we did before? Is that if you apply this thing to v of z equals minus z, then ft of z is equal to e to the minus t times z. So you recover the annulus at from before. So you have a way to, if you wish, you can think of these vector fields as the Lie algebra of a semigroup of annuli. And we want to play the same game and associate an operator to each such annulus. So this we can do. So well, actually, this is what I wrote. And so now, what is the operator that you associate? Well, I just defined for you an annulus with boundary parameterization, and I can associate the operator with kernel at, and the metric is the same as before, and these boundary parameterization are zeta 1 and zeta 2. Okay, and actually, so again, just by the gluing rule of Segal axioms, you can check that this is going to give you a one-parameter semigroup of operators on your Hilbert space. And again, sorry for the typo, it should be the subword space H minus epsilon. And there is actually a formula for this. There is actually an easy formula for this operator that I can write down. So if I apply this operator to a function and I evaluate it on the field phi, this is actually going to be equal to e to the t q square over 2 b prime of 0. So there is a funny prefactor. And then I take the expectation with respect to the GFF in the disk of f of x composed with phi t plus q log z ft prime over ft restricted to the unit circle. Yes. And I multiply by the potential. And this is on the annulus AT.
So can you read the formula Q ln slash?
It's a logarithm of modulus. So this is modulus ft prime over ft. Yes, and this is conditionally on the fact that my field restricted to the unit, to the boundary of the unit disk, so the unit circle, is equal to phi. So for the probabilist in the audience, it's like if you try to solve the heat equation with Brownian motion, you start from an initial condition, so here which is a field phi, and then you look at the Brownian motion. So here the Brownian motion is replaced by this field in the unit disk, and you evaluate your Brownian motion. So you run your Brownian motion until it reaches this curve, and you evaluate the field on this curve. So you can write an explicit formula for this operator, and you have to reweight by. So this is a sort of Feynman-Catch formula. You reweight by the total mass of GMC in the annulus. But if you don't like this expression, you can just recall that we have defined some amplitudes, and you can use the gluing property of the amplitude to just deduce that this family of operators is a one-parameter semigroup of operators on the Hilbert space, from which we can extract a generator by Shida-Yoshida. And this is what I'm writing here. So it is a semigroup. You can extract a generator, and we can actually have a formula for these generators. Yeah, there is a formula for these generators, but so the generator is called HV, but I'm not really satisfied with HV because you can check that the mapping V goes to HV depends real linearly on V, and I want to extract. I want to have a complex linear dependence on V. So this is what I'm doing here. It's like if you define dz to be 1/2 of dx minus I dy, well, I'm doing exactly the same thing here. So this guy depends real linearly on V, but this guy is going to depend complex linearly on V. And I can do the same with the L tilde, which is now going to depend complex antilinearly on V.
Yeah.
Yes.
V is your vector field, right?
Yes, E is the vector field.
So you add a condition on the real part of V over Z?
Yes, so you can check that if you add a large multiple, so basically you're defining a cone in the Lie algebra of vector fields in the disk. But if you add a large multiple of this guy, you will always have this condition.
Yeah, but what about IV?
Yeah, so yeah, maybe so now if you pick a small cone around the real line, you can always pick a small cone around the real line, and so you will shift the argument of this guy, and so then it's sufficient to. So essentially, this cone is generating all possible vector fields. So you just define it by okay. So you can define these vector fields in this cone, and then you can extend the real linearly to all vector fields, and then you do this extraction. But yeah, thanks, that's a good question. And almost by construction, these guys are going to represent the Virasoro algebra. Well, at least what I did is that I only had holomorphic vector fields in the disk. So a priori, I don't have all meromorphic vector fields. So actually, the notation here is that Ln is the operator that I associate to this vector field. And these, almost by construction, are going to represent the Vit algebra. But a priori, this is only defined for n bigger than 0. And what I do is I can define even Ln, L minus n to be equal to Ln star. And then you can check that these, at least when mu equals 0, it's very easy to check that they are going to represent the Virasoro algebra. And actually, when mu equals 0, not only do they represent the Virasoro algebra, but they are something very canonical because they are the Fagin-Fuchs construction of the Virasoro algebra. So here we have a underlying Heisenberg representation, and these expressions for mu equals 0 correspond to the Fagin-Fuchs construction of the Virasoro algebra. And actually, to extend this to mu different from 0, it takes some work, but you can do it. And you can prove that the commutation relations are preserved. Yes.
So for Ln tilde, you define them similarly with the complex conjugate?
Yes. So there is a better way to define it, but I will not really say how you do it. But basically, what is the adjoint? The adjoint is so the kernel of the operator is so you exchange the two variables, and geometrically it amounts in flipping the annulus somehow. So you associate the operator to the annulus that you have flipped. So you exchange the two boundaries.
Is there a reason you don't use L bar?
You have to ask Rémi and Nancy, I think.
It's in physics books. I think it would be L bar.
Yes, I agree, but I'm gonna use a joker for this. Yeah.
Well, it's the same.
So what did you say about functionalization of representation?
Yes, so there is an under. I can say a few words about this. So we were writing the field as a sum of modes, sum of phi n into the I n theta. And you can define two Heisenberg representations if you want. So maybe I'm going to call it an equal I over 2 d. So you differentiate. So this is an unbounded operator on the Hilbert space, which is a complex derivative in direction phi n, and a minus n is a n star. So these satisfy the Heisenberg algebra, and the Fagin-Fuchs construction is that you define Ln to be, so this is going to be for mu equals 0. It is minus iq n plus 1 a n plus the sum for m for all integers n of a n minus m a n, where these things are the Wick normalization, and this gives you a Virasoro representation. And what I'm saying is that for mu equals 0, these operators coincide with the Fagin. So the operator that you obtain as a generator of the semigroup is the same as this operator.
It's also called maybe Sugawara construction sometimes?
Yes, but I think that some people like Sylvain might disagree with this. So sometimes Sugawara. So I think some people only use the word Sugawara for when you have a non-Abelian group. So here it's basically Sugawara for G equals S1. Okay. And yes, and by construction this is unitary, but I just told you that you can also construct this ln star in a more geometric way if you want, but I'm not going to talk about this. So you have, yeah, so basically, to sum up what I've just told you, is that you, just by using Segal axioms in the special case of the semigroup of annuli, we were able to extract two commuting Virasoro representations acting on the Hilbert space, which are just the generators of this infinite dimensional semigroup. And to do this, you basically apply the Hiro-Yoshida theorem, but for this infinite family. Okay. And so now let's focus on the special case where H. So the special case is that the Hamiltonian is L0 plus L0 tilde. Well, this, because Ln star is L minus m, this guy is self-adjoint. And it is the generator of these of this semigroup, which is just contracting annuli, which are just straight cylinders. And what we want to do is to diagonalize this operator. And this is something also that was done by Colin, Anti, Rémi and Vincent. So you have an explicit expression for this operator, which is just, so you use the Fagin-Fuchs representation that you evaluate at n equals 0, and you get this. So at nu equals 0, you just get this harmonic oscillator, and you add the potential. So actually, there is a general formula, which is that Ln is Ln at mu equals 0, so the Sugawa representation, plus mu, the integral of e to the gamma phi, so of e to the ni theta d theta. So if you wish, these are the Fourier coefficients of this GMC. So you have this this harmonic oscillator in the n equals 0 case, so for the Hamiltonian, and the potential, and for n different from 0 there is a twist, but we don't really want to look about n different from 0, so we're just going to look at this potential. And this potential is just a multiplication by a positive thing, so you remain positive. And it's actually a very hard theorem to diagonalize this operator. But it was somehow done, and I think this is probably going to be repeating. But yeah, so we want to diagonalize this operator, and what I want to explain is that basically the eigenstates of this operator, you can understand them as Segal amplitudes of disks. And how do you justify this intuitively? So you start with an amplitude in the disk with some weight alpha inside, and just applying this operator to this amplitude is going to glue the green disk to the red, the green annulus to the red disk, and you still get a new disk. So when you glue a cylinder to a disk, you get a new disk, and so this is again an amplitude of a disk. So up to a scaling factor, you just get another disk amplitude. And so there should be so this guy should be an eigenstate with some eigenvalue delta alpha, and yeah, so this is a heuristic argument to say that well, almost even a proof actually, that amplitudes of disk are going to be eigenstates of the Hamiltonian, and this is actually the case. So what you have. For the spectrum of this guy, is so you're going to get a complete family of eigenstates, which are indexed by this line. So you have 0 here and q there, and the half line q plus ir plus. So this is the spectrum. And these eigenstates, they are indexed by two things. So this spectral parameter q plus ip. And they are indexed by pairs of Young diagrams, mu and mu tilde, and the eigenvalue is this guy. And what we call, so earlier we were writing the eigenvalue as delta alpha, but now when delta alpha is actually alpha over 2 times q minus alpha over 2, which in particular means that delta q plus ip is q square over 2, or over 4 maybe, plus p square over 4. And this is the two, so this part is 2 delta q plus ip, and the length of the Young diagram is going to be the eigenvalue also. And why is this family complete? It's because you have this Plancherel formula. The Plancherel formula tells you that if you take two functions in the Hilbert space, you can just write it as this formula. So what is this formula saying? So if we were just in R on the real line, we would just get this integral, and we would do a Fourier the Fourier Plancherel formula, which would just be pairing the two functions with just plane waves. So this is the first part of the formula. You pair the functions with plane waves, and then you actually have to sum over these Young diagrams. And these eigenstates, they are not orthogonal, orthonormal, so they are, which means that you have to reweight by this so-called Shapovalov form, which has some algebraic meaning that I will explain. So you can actually write the pairing of two functions as this. And so there is this thing where the Shapovalov form appears. The Shapovalov form is related to the representation theory of the Virasoro algebra. And there is a reason for this, which is not apparent in this theorem yet, is that these eigenstates, they are obtained by the action of our Virasoro representation on the primary fields. So the primary fields are what you have when you put nu tilde equals 0. So again, what is not stated in this theorem is that these eigenstates are the descendants of the primary fields, which is actually what we were able to prove in a subsequent paper. So there are actually two parts in the statement. So a priori, I only define these psi q plus ip on the spectrum, but you can actually analytically extend them to the whole complex plane. So historically, this was done in two parts. It was first done, so you pick an alpha here that is very negative, and in this region, so alpha very negative. Here you have a probabilistic expression for these guys. Well, actually, just for alpha less than q, let's say, you have an expression which is a probabilistic one. So it looks like a plane wave at first in the zero mode, but then you reweight by the total mass of a Gaussian multiplicative chaos in the disk with some singularity at 0. And again, you condition on the fact that your field on the boundary is equal to phi. So you have a probabilistic expression for the primary field. And actually for the descendant fields, you also have some probabilistic expression, but for alpha very negative. Yes. So here I think I'm on mu e to the gamma c plus c. And Rémi told you yesterday that for this singularity to be integrable, I need alpha less than q, which is why I require alpha less than q here. So you have an expression here. You can prove that it has an analytic that this probabilistic expression has an analytic continuation in the neighborhood of this half line, and actually that this analytic continuation includes the spectrum, so that you have an analytic continuation in some region like this. And what we did in the subsequent paper is to prove that this analytic continuation is actually valid in the whole complex plane, so that you have a family of eigenstates which is indexed by alpha complex.
Sorry.
Yes.
So does it give you the freedom to modify the spectrum by deforming your half line?
So I think there are two questions in what you're saying. So I have an operator on a Hilbert space. So the spectrum is the spectrum full stop.
Maybe you can also modify the Hilbert space.
Yeah. So there are three questions maybe. Then maybe the question is if I want to do some bootstrap, can I deform the contour when I integrate? That's another question. And the last question is if you want to modify the Hilbert space, I don't know, do you want to include logarithmic fields or stuff like that? There are many ways to change the Hilbert space, but then I'm not sure what. Depending on what you want to do, you would modify it in a certain way. Yes. So, for example, if you want to include, so here in the zero mode, I have to be bounded somehow. If you want to include polynomials, maybe you would have some logarithmic fields also in the spectrum. Does that make sense? Or yeah. But for now, I really want to have a self-adjoint operator acting on my Hilbert space and diagonalize it. Right. And yes, and so what we did is to prove actually that the descendant state, so when nu is when these two Young diagrams are not zero, these eigenstates are really the Virasoro descendants of the primary state. And in particular, you can construct some highest weight representations. That are, if you put nu tilde equals 0, you get some highest weight representation, so actually if you're not on the catch table, you know that this thing is going to be a Verma module. What I proved also is that if alpha is on the catch table, you get some irreducible quotients. This is for alpha on the catch table. Okay, so you get some states like this, so the spectrum is here, but you have no probabilistic expression for it. And when on this region on the half line, you get some probabilistic expression with which we can work, and there is this interplay of how you go from the probabilistic to the analytic regions. Okay, so this gives you essentially all the structure that you want. So to sum up, you have a Hilbert space, a Hamiltonian, and two commuting Virasoro algebras, and you are able to diagonalize the Hamiltonian using the Virasoro algebra.
Does it make sense to ask how to construct this psi, like your psi alpha 0, 0? Construct means not define it probabilistic, but some more explicit construction.
So for me, this is very explicit actually. But I don't. How explicit in terms of what like?
That's a good question, but
maybe the intertwining by the intertwining.
Yes. So okay. So that's a good point. So you have the ln0. So okay. So I'm not sure if it's going to help, but so okay. So you have some free field eigenstates, which are just this prefactor. And really, the way you can think of, I'm not sure it's going to be helpful, but so yeah, you want to say that I'm not sure it's going to because
just with the Hamiltonian. This is eigenstate for the free Hamiltonian.
Yes.
And then you propagate.
Yeah. So these are the eigenstates for the free Hamiltonian. What you do then is you apply you look at the long time asymptotic of the free Hamiltonian. So but this is just scaling. So you rescale by the good thing. Here I put a new, and then you apply the Hamiltonian to this, and this is going to converge to st goes to infinity to this eigenstate. But this is only true for alpha actually in the probabilistic region. So that's what I think what Colin was saying. So yeah, you can. I'm not sure how. Okay, so this is relatively explicit, I'd say, and at least it's something you can work with. So if you know about GMC, you can handle this kind of expression. So for us, it is explicit, I would say. Okay, maybe one last property of these guys is that they satisfy a reflection relation. Where this R of alpha is an explicit expression in terms of gamma functions, which is called the reflection coefficient. And it is independent, crucially, of nu and nu tilde. Okay, so maybe the interesting thing about the proof, and I think it tells a lot about the mechanism that we use, is that when nu and nu tilde are both equal to 0, it's something you can prove using probability theory that this is going to be true, and then you use you apply the Virasoro descent operators to both sides, and you can check that you have the regularity properties that you need to obtain the same formula for the descendants.
So one question I have, like for correlation function or for blocks, like sometimes like when you choose the alpha to be some specific value, like then you get a Silberg type integral. Is it also true for this chi function, the eigenfunction?
So say at the end.
Like for instance, if you take this alphas, the weights to be in a specific way, you get a correlation function, a Silberg type integral formula for the correlation function, right?
Yes.
So is it also true for the chi, this function?
For the what?
The chi function that you define.
For the chi function?
So chi alpha c plus phi.
Psi alpha, you mean?
Yeah.
No, this is. I don't think it's. I mean, it's a function in the Hilbert space, so it's not. I mean, a Silberg integral is a complex number, right? So.
It's an expectation of something, so I was wondering.
It's a conditional expectation. So it's a function of the field.
You don't get a number, like what?
So you get a number if you pair it with another state. And then actually the pairing of two states in the Verma module will be just the Chapeau-Wallah form. Okay, so in the next 6 minutes, I will start discussing.
You have
21 minutes.
20 minutes, 25
I
minutes.
thought there were 15 minutes for questions.
No, it's okay.
I'm also happy to stop at. I had planned to stop at 42, so. Okay, I'm going to a new part, but I will start the part and just see if there's some points to stop. Okay, so now what we want to do is we want to construct conformal blocks, and the conformal blocks, they are going to be obtained from matrix elements of from pent amplitude. So I will just give you the main idea at first and then explain why we want to do this. So suppose you want to compute the amplitude of, I'm going to put some color here. So suppose you want to compute the amplitude of this surface. So you can cut this surface along some curves, and you get two pairs of pens. And just by Segal, this is just the gluing of two pens. And the gluing of two pens is just the pairing of two. So the partition function of this surface of two pent amplitude. So maybe I have one pen P1 and one pen P2. And I'm going to look at the inner product of the amplitudes of AP1 and AP2. Okay, but so now these are elements in the tensor product. So threefold tensor product of the Hilbert space. And what I can do is I can refine this inner product to look at by looking at the spectral resolution of these amplitudes. So my spectral resolution allows me to project on each Verma module because what I have just shown, and what I have just explained is that the Hilbert space can be written as an integral from 0 to infinity of this VQ plus IP, tensor VQ plus IP bar. And so what I want to do now is to project the amplitudes on each Verma module. And instead of pairing the two amplitudes, what I can do is I can pair their projection on these Verma modules, and this is going to give me the conformal blocks. And this is what I will explain until we eventually get hungry. So the key to this thing is actually that these amplitudes are going to have some holomorphic factorization. So what do I mean by holomorphic factorization? Is that I have a modular space of pairs of pens with boundary parameterization. This is an infinite dimensional space which has a complex structure. And so it makes sense to talk about holomorphic functions on this modular space of pairs of pens. And what we will show is that these pen amplitudes are actually admit a holomorphic factorization in this space. So let me make this a bit more precise. So I want to use a very special kind of uniformization for my pair of pens. So I can always find a chart that will map this to the disk, to the sphere, sorry, minus 3 analytic disks. So maybe I can do one disk. So there is one disk that contains infinity, one disk that contains, say, 0 and 1. And the way I choose this uniformization is that these are really the sphere minus 3 disks. So I put one map here, so let's say psi 1. Psi 2, and one map that uniformizes the exterior of the disk. So I can always represent a pair of pens by this kind of uniformization. So I take the Riemann sphere and I remove these three analytic disks, psi 1 of D, psi 2 of D, and psi 3 of D. And the parameterization are as before, so we just use these conformal maps to parameterize the boundary. And I choose the metric in a certain way so that locally it looks like this flat metric. And I can express the amplitude with respect to the GFF. So this is the key thing is that now I have these curves that are embedded in the sphere. And in the sphere, I have the GFF, which is defined on the whole sphere. And what I can do is I can restrict the GFF to these three curves. And this gives me three fields, which I can view as fields on the circle by pulling them back with these conformal maps. And the amplitude is really the low of these three fields viewed as fields on the circle. So the amplitude of P is the low of GFF on curves psi j of x1. Viewed as fields on the circle. So it's really with respect to the tensor product mu 0 cubed. So I can view these fields as fields on the circle. I get three fields. This measure is absolutely continuous with respect to my canonical measure, and this gives me a measure, and the amplitude is really the same thing as this thing. And now, so I will just talk about this variation of amplitudes and stop here, I think. I'll talk about the holomorphic factorization later. So now, okay, so now I have my moduli space of pairs of pens, which is just a pair of 3 embeddings. And my question is, how do I deform these embeddings? So I can think of at least 2 ways to deform the embeddings. I can pick a flow of deformations that I generated earlier with the semigroup of annuli, which means that I can look at I can contract the disk with some flow of conformal maps like this. And when I look at the embedding, it will be some curve inside, and this gives me a way to deform the pair of pens by looking at the and infinitesimally I can look at this T small, and it will give me a curve that is infinitesimally close to the blue. So I can do this, or I could also rather pick a conformal map on the sphere and deform the blue curve just by post-composing my psi. So I can either pre-compose psi with FT, or post-compose psi with some conformal map defined in the neighborhood of the curve. But in any case, if I do this first thing, I get a new parameterization, which is psi j composed with ft. So this describes the tangent space of my Teschner space. So now maybe I want to change a little bit the way I deform, and instead of deforming with a flow which is nicely conformal inside the disk, maybe I will just ask ft to be if I just ask ft to be conformal in the neighborhood of S1, so away from maybe some neighborhood here, then it is not true, as I wrote here, then it is not true that if I use the parameterization psi j composed with ft, then this is no longer the sphere minus 3 analytic disks, because this psi j composed with ft is not conformal. So I need to reuniformize my guy, and this is what I'm saying here. So now if I move if my ft is conformal only in the neighborhood of S1, I need to reuniformize my pair of pens by finding a conformal map that will map me to my model form, and the new parameterization is this thing. So it's psi j composed with ft, but I need to post-compose with some guy here, and the metric is no longer the usual one, but it's the pullback of this metric by phi t. And in fact, now you can look at the variation of the amplitudes. And in the case where my flow is nicely holomorphic inside the disk, just by Segal, I'm gluing an infinitesimally small annulus here, and gluing an infinitesimally small annulus is the same as composing my amplitude with the flow, and infinitesimally the flow is just the Villarsot algebra. So when I just by Segal gluing the Segal axioms, when I vary the pair of pens with some nice holomorphic flow, it's just going to compose the amplitude with some Villarsot operator, and I have the same t-bar extension at order 1. And actually, it's true. It remains true if you look at not a nicely holomorphic flow. So this line should not be here actually. There's no Schwarzenegger derivative here. So yeah, just by these Segal axioms, you have a way to understand how the amplitudes are varying, which is just that when I vary the pair of pens infinitesimally, it's the same as composing with the Villarsot operator. And there is a special case of this transformation. So there is a special case where maybe I will move all of the curves in a certain way that the pair of pens is still conformally equivalent to P. But now, in this case, my pair of pens is related, so I have just changed the metric conformally with respect to G, and I can use the Weil anomaly. And now the variation of the Weil anomaly is this expression, and the derivative of the Liouville action is just the stress energy tensor, and when you have a stress energy tensor, when you specify to a conformal map, it actually gives you a Schwarzian derivative. So you have two ways in the special case where the pair of pens is conformally equivalent to P. You have another expression for this. You have another expression for this variation, which is just a correction, which is a Schwarzian derivative. So when you put these two information together, that the variation is composing with the Virasoro generator, and that if you are conformal, you get a Schwarzian derivative, you get this expression which are just the word identities. That the sum of the LBJ, so AP composed with LBJ, is equal to some Schwarzian derivative, and this condition of being conformally equivalent is really the same as the fact that these pullbacks of these vector fields, they extend. These push forwards, they extend holomorphically to the whole pair of pens, and this is a form of the usual word identities that you find in VOA groups, for example, but rephrased in analytic setting. Okay, so I think it's already a mouthful, so I will stop here and maybe continue on explaining how we go from word identities to this holomorphic factorization tomorrow. So remember that we have a space H, which is an L2 of so but it's space on the circle, and the measure is the big measure on that 0 log, and a measure which is the logarithmically correlated field on the circle, and samples are denoted phi. So this is the field on the circle. And what we did last time was to construct a family of operators acting on this space. So we have ln tilde, or ln bar if you prefer, which are two commuting Virasoro representations. Acting on this space. And we were able to write this space using these Virasoro representations. And so you can write that this is the integral from 0 to infinity of some tensor product of Verma modules. And this guy is a Verma module. Which is equal to the linear span of some eigenstates of the Hamiltonian. Remind you that the Hamiltonian is L0 plus L0 bar, which is self-adjoint. And we were able to diagonalize this operator, and we can write the Hilbert space as a span of all the eigenstates, and we were denoting them by psi q plus ip nu, where nu is a Young diagram. For an integer partition. And this guy is just obtained by acting with the Virasoro operators on the primary field, which is just psi q plus ip. So this is the basic data that we have. And the way we were able to construct this Virasoro representation was just by extracting the generators of the Liouville of the semigroup of the semigroup of annuli. So we have a semigroup of annuli. We associate amplitudes to these annuli, and the generators of this semigroup are our Virasoro operators. And then so we were looking at pairs of pens. And so the way I wanted to parameterize pairs of pens was by removing 3 analytic disks to the Riemann sphere. So this is so a pair of pens is So the domain is the sphere minus the union of three analytic disks. So the union of psi j of the unit disk. And this gives us a way to parameterize pairs of pens, and I can have marked points here, which is where I send 0. So I would have z1, z2, z3. And so I can also choose a background metric on the whole Riemann sphere, which needs to satisfy some properties, but I will not talk too much about this. It's also in this case here. And now we want to, so the integral picture, we associate an amplitude to surfaces with boundaries. So, and so here the parameterization of the boundaries is just psi j of z, is just, well, given by the parameterization induced by the conformal maps. And now the amplitude that we associate is basically, well, I mean, if you really want to have a short take-home message, the amplitude is, so if mu is equal to 0, this is just the joint law of the GFF in the whole sphere, restricted to the curves psi j of this one. And if mu is not equal to 0, this is just the same, but reweighted by exponential of EGMC. Of the GMC in the pair of pens. So it's just basically from mu equals 0, it's just the, so I pick my GFF, I restrict to the curve, I see him as three fields on the circle using these guys, and I express it as a Radon-Nikodym derivative with respect to my canonical measure here. And this gives me an object in the Hilbert space to the power 3. But since it's a measure, it's also nice to see it as a linear form on h to the 3, but which is the same just by Riet's theorem.
Can you recall what is mu?
Mu is so it's just a coupling constant, if you wish. It's
but where it is in this picture?
In the action. So the Liouville action was.
Okay.
You can think of it. You can think of mu equal to 1.
Do you have the action functional in the slide? Can you show it? Because you can just reveal behind the blackboard.
Yes. So maybe I can just write it. S sigma of phi g is the integral of so plus q Ricci curvature times phi plus mu integral of gamma phi dvg. So mu appears here, and it's the coupling constant that gives you the exponential. Okay, so now the goal of this talk is to explain how we compute this guy and prove some kind of holomorphic factorization for this guy. And so this, I told you, is really an element of h to the 3, but I want to see it also in the dual, so h prime to the power 3. Which means that I can pair this guy against some primary fields or descendants, and what we want to do is to compute these matrix coefficients. So what happens when I pair this guy against some descendant states?
Sorry, so the reweighting also depends on gamma,
yes.
which gives the central charge, right?
Exactly.
Yeah.
And so okay, so now the goal is to compute these guys. So I want to pair my amplitude against the primary states and their descendants. And I'm going to explain to you that we have basically two tools. So the fact that what I wrote here, that these descendants are obtained by acting with the Villarsot algebra, and the word identities, which I explained yesterday. And so to give you the results already, we're going to obtain some sort of a holomorphic factorization, which means that when you pair the amplitude against these descendants, well, up to a constant, which depends on the structure constant and the metric that the background metric that you choose, this is just some holomorphic function on the space of pairs of pens, and factorized with a product with an anti-holomorphic function. So you have a complete factorization in the new and the new tail guys. And once you have this, in fact, once you have this, then you can write that this amplitude is really an integral over the, well, r plus to the 3, so 1 r plus for each boundary component of this structure constant, and some guy now that lives in the Verma module, so this BP would be a holomorphic function in the Verma module to the power 3. So this is what we want to prove, and so I actually told you that we're going to use the word identities, and I think that I was a bit fast yesterday, so I'm going to remind you how we reach the word identities. So the word identities is what happens when you want to move this pair of pens infinitesimally. And there is one special transformation that you can do, is to pick a conformal map that is defined in the neighborhood of your pair of pens. So phi t, it's going to be, so I want to pick a conformal map that is close to the identity, and that is generated by some vector field, so phi t. Right. This guy would be V would be a holomorphic vector field in neighborhood of the closure of P. And so when I look at the flow generated by this guy, it's going to give me a pair of pens which is conformally equivalent to P, which is going to be Pt. But I could also view it as, it's the same pair of pens conformally, but the metric is slightly varying because I'm looking at the metric, the pullback metric. But I could also view this as moving each curve separately. And when I move the curve, when I move each curve separately, I'm moving slightly inside my moduli space of pairs of pens. So I have two ways of writing the variation of this guy. So the first is using the Weil anomaly. The Weil anomaly tells me that I'm going to obtain the same AP up to something that is proportional to the central charge. And when you differentiate at t equals 0, you get actually that this is I might be off by some constant, but I think it should be yes. So you're going to pair your embeddings with the vector field. And here, what I call Vj is the pullback. Is the pullback of my vector field inside the disk, so by psi j. So Vj is psi. Is the pullback of V by psi j, which is V composed with psi j over psi j, right? So this is the first expansion that you could write. And the other expansion that you could write is Schwarzian derivative. The other expansion that you could write is say, okay, well, actually what I'm doing is that I'm just moving each of the embeddings infinitesimally. And we saw yesterday that moving the embeddings is essentially inserting a Virasoro operator. So I have another way of writing this, which is it's also equal to a sum from 1 to 3 of my amplitude AP composed with LV, LVJ, plus a little o of t, plus t bar AP composed with VJ, plus a little o of t. So now you identify the t and t bar apart. It gives you that the sum of AP composed with LVJ is equal to some Schwarzen derivative. It's so this is in one line how you derive these identities.
But APT should reduce to AP at v equals 0, right? So
no, so AP APT is some exponential, so there is some Weil anomaly, Weil times AP. And when you differentiate at t equals 0, so this Weil anomaly depends on t.
No, but the way you wrote, it vanishes.
Ah, yes, sorry. Okay. So yeah, this gives you when you identify the other one, you get what you want. Okay, so now we want to use this tool to obtain this sort of factorization.
So here when you mean LVJ, it's like the J component derived from the J's component of the tensor product.
Yes, so it should be maybe
it's like identity.
Yeah, exactly. You're right. Okay.
And LVJ, what was LVJ?
So the LVJ is the pullback of V to
the sum of V of the coefficient.
Yes, so I think yesterday I wrote LV. So if I have a vector field, LV is the sum of so if I write the expansion of V as Vn z to the n plus 1.
Can you write it?
Yeah. Okay, so if my V is the sum of Vn z to the n plus 1, LV is sum of Vn Ln. Okay, so we want to do this.
So may I ask general question? Maybe yesterday you responded it. So in both formula you make complex alphas, right?
That's a very good question. So note that yes, I was going to mention this next. So on this board there is no alpha, right? It's a linear form on the Hilbert space, and then I'm going to compute it on some specific alphas. And precisely what I was going to explain in the next slide is that you a priori you cannot. So in the probabilistic expression, you cannot put alpha equal to cosine. You're not allowed to put to be on the spectrum. But you need to use alpha real and then analytically continue. But this is what I'm about to explain now. So let's, as a warm-up, let's look at what happens if we want to compute the amplitude evaluated on primaries. So the two Young diagrams are set to 0. So I cannot use my probabilistic approach to compute this on the nose, but I have to be in the region where I can do probability, which is the region alpha less than q, which was the one of the bounds that Rémi mentioned in the first lecture. And just by the Segal axioms, this is very easy actually to compute, because when these psi alpha, they are nothing more than amplitudes of disks, as we saw yesterday. So computing this thing is just gluing 3 disks to my pair of pens, and I obtain the sphere with 3 marked points. And so I obtain just the correlation function of the sphere with 3 marked points, alpha 1, alpha 2, alpha 3. And this is going to be up to some product, up to some factor in Z1, Z2, Z3. This is just the DOZZ formula. And you see that this is the modulus square of some multi-valued meromorphic function, or actually, yeah, it's a multi-valued holomorphic function away from the marked points. So we're already seeing the holomorphic factorization that we want. But note that this, if I want to remove the modulus, I get a multi-valued function, but which would be holomorphic away from the Mark codes. So okay, so we have a way to compute the amplitude on the primaries, and we just obtain up to a prefactor those formula some holomorphic factorization. Okay, and now the question is, how do we compute descendant states? So now suppose we can do this by induction. So now if I want to compute AP paired with L minus N psi alpha nu so now suppose I want to compute this sort of thing with some n positive. So I want to actually use what I wrote upstairs. So L minus n corresponds to looking at. So what I can do is I can generate this sort of deformations using a V that is holomorphic in the neighborhood of P. But in particular, nothing forbids me from taking a V that is holomorphic, well, let's say meromorphic in the whole Riemann sphere, with poles only at Z1, Z2. In particular, I can use a meromorphic vector field in the whole sphere with just a unique pole at Z1. And this would generate this would amount to applying some L minus n here. So just by word identities.
So there is no topological abstraction for the pole structure of vector.
No, so on the sphere you can have on the sphere if you have a meromorphic if you have a mixed vector field with a pole, a simple pole, you can always extend it to the whole Riemann sphere. But of course, this works because you're in the sphere. It would not work on higher genus, for example. And you are allowed to have, if you have just one pole, you can extend such that it is also regular at Z2, Z3. Well, you just take Z to the minus n, you expand it, and you check that it's regular everywhere. Okay, and so just by the word identity, so I can just use this kind of formula. It would tell me that this is equal to my amplitude paired against some psi alpha 1 mu1 tilde tensor, sorry, some LV2 psi alpha 2 mu 2 mu tilde 2 tensorized with psi alpha 3 3 mu tilde 3, and I have same thing. So here I have the same tensor now psi alpha 2 mu tilde 2, and now I have another vector field. And right, and plus some sum of Schwarzschild derivatives. And but now the crucial point is that these two V2, V3, they are now holomorphic. They are holomorphic at 0. So which means that we are going up in the Verma module instead of going down. So it means that by induction, that I can implement an induction here, or if I want to compute the amplitude against descendant state, it's this, I can express it as an amplitude against guys that are unknown. So this means that this is my unknown coefficient, which I can express in terms of known things. So this tells you that you can compute things by induction. and you arrive at what you want, which is that. So now the induction will tell you that you have some coefficients like this, which are depend holomorphically. So you know that it's true for the primary state, and now by induction you deduce that it's also true.
So this is because when you apply L with positive n, you decrease the Liouville by commutation.
Yes, exactly. Yeah. So L minus n is so you have your Wehrmann module.
Like annihilation.
So you have your Wehrmann module, which is something like this, V plus IP. And when you apply with some negative n, you go down, and when you apply positive n, you go up in the Wehrmann module. And so since these guys have positive n's, you are going up. And so for coefficients that you already know. So you have a way to implement some induction. And as was mentioned earlier, you cannot. So you have to first apply this in the region, in the probabilistic region where you have some control and some expressions, and then analytically continue this expression to the spectrum, and you get the same formula. Okay, and so in the end, we have written that this amplitude is some constant that depends on the metric times the integral of our Diozisi formula and some holomorphic elements in this product of Wehrmann modules times an anti-holomorphic guy. Yes.
How you make sure that the integrals make sense?
Okay, so this it's a very good point. So this guy, we know from the spot that it's L2. So the existence of such a decomposition is given on the nose. So we know a priori that...
Do you use the explicit form of those?
Not really. So we know from probability that this amplitude is in L2. So it has a spectral decomposition like this. And then you compute the... So you know that such a decomposition will exist. What you don't know is that it will have a holomorphic factorization like this. So when you compute the coefficients, you get...
It's because of Planchtel formula, so it's like
yes.
Fourier coefficient. This W or like Fourier coefficient?
Yes, yeah, exactly.
In terms of the Young diagram?
Yes. So there are Fourier coefficients. So we know that such a decomposition exists. And then what we don't know is that the Fourier coefficients have a holomorphic factorization. But we prove this by hand using this coefficient.
So the integral is absolutely convergent?
Yes, that's actually something I was going to come back later, because it's used to prove the convergence of conformal blocks, for example. Okay. And now we know how to compute the amplitudes of bands and know their spectral resolution. But now what we want to do is to compute conformal blocks. And now we're going to look at compact surfaces. And I'm going to focus on the example of genus 2, as I already mentioned yesterday. So in genus 2, we can cut a surface into two pairs of bands. So here G would be a graph which is encoding a topological choice of band decomposition. So I fix such a topological choice. But so this is just giving me a family of homotopy classes of curves. But then I have a freedom of choosing any curve that I want in this homotopy class. And once I choose such a representative in each homotopy class, I can uniformize each pair of bands to my favorite form, which is the sphere minus 3 analytic disks. And so I have two bands, P1 and P2. And I know that AP1 and AP2, so the partition function of this surface, with maybe some metric, is a pairing of two bands. And so using my formula from before, I can say that this is the integral over r plus to the 3 of some metric constant. And then I have my DOZZ formula. So I have two DOZZ formulas actually, which I'm just going to write like this. But more importantly, I have a BP1, P, BP2, BP2. So P now is the spectral parameter. P1, P2. Against BP2, P2. But this is in the product of Verma modules. So in the Verma. So I can use what I did before to write this kind of decomposition. And
so here it's a self-gluing of Manton, no? So it's not exactly the pairing.
Yes.
It's like a trace.
Yeah, it's a trace. So
or maybe you can write.
Yeah, I can.
You can glue to sort of thing.
Okay, let's say that it's the trace. It's the trace according to my graph of BP 1 and BP2 P2 and times the integral of 1. And what I integrate here.
The reason the trace exists?
Sorry?
What is the reason the trace exists?
Again, everything is L2, so it will exist for almost every P. So this, so for almost every value of the spectral parameter P, this trace will exist.
In the strict sense. In the strict sense, as a trace class operator, or
yes.
So this trace is a number actually. So if you
think the B or the Hilbert-Schmidt.
Yeah,
the B or Hilbert-Schmidt in the Verma module. Actually.
Okay, I see.
So when you can trade.
But in fact, what I'm really interested in is actually the holomorphic parts here, and this is what I want to define as the conformal block. So this is going to be F sigma G P of and a priori this also depends on this whole data. So this of this whole data, which is and also it includes the choice of Pence decomposition, which I denote by psi. So this is going to be the choice of curves. So this will depend on my psi, but this I want to define it as the trace along G of these BP1 and BP2. Okay. Yes, this is what I wrote here actually. So if you choose a surface and you do the trace along your graph of all your blocks, then you get some product of DOZZ formula times this function, which depends on the full data. But now it's kind of annoying that a priori this conformal block depends on the choice of curves, because ideally conformal blocks, they have to be defined on the Teichmüller space of sigma, not on the Teichmüller space of sigma plus Pence decomposition. So I need to remove this dependence, and actually I cannot quite remove this dependence precisely because of these Schwarzian derivatives that appear. So there is some anomaly that I have to take care about. And this is why we can only define blocks as sections of a line bundle over a Teichmüller space, and not as a function on the Teichmüller space of the compact surface. So this is what I wrote here. So a priorities depend on the whole data, but now we want to get down to the Teichmüller space of the compact surface. So here I have a data that depends on an infinite dimensional space of parameters, and I want to bring it down to a finite dimensional space. Okay, so let's try to vary the let's try to vary a bit the choice of pens decomposition. So I'm going to pick a fixed size 0 pens decomposition. I vary it slightly by some holomorphic vector field in the neighborhood of the curve, say. And I use the conformal word identity. So I know that when I differentiate my, this would be f, sorry. When I differentiate this guy, I will obtain sums of shortened derivatives that come from these Weil anomaly. But it turns out that this sum of shortened derivative, it's actually going to be a differential form. So you can view it as a differential form on this space of, on this stationary space of surfaces plus pens decomposition. So it's a differential form on this infinite dimensional space. And you can wonder if it's closed or exact or if it's closed. And actually, if you look at pairs of pens, you get this Schwarzian, but if you differentiate the Schwarzian, you will get a Virasoro cycle. So you might think that it's not going to be a closed form. But in fact, since when you pair two pens, well, you have some commutations, and this is going to be a closed form. So you can say that this theta is going to be the differential of some epsilon, which is
J and
so sigma is a smooth topological surface, and J is what it's just it's a complex structure.
And this you want to keep in the.
So yeah, so now I fixed the J, and I vary so with a fixed complex structure, I want to understand how my block is going to vary with respect to the choice of embeddings of curves. And I can see that it's going to change in a controlled way, and I can actually construct a cocycle such that this theta is a differential of the cocycle, and which means that if you pick two different choices of curves, you integrate this differential form, and the two blocks are related by this cocycle in a controlled way. And you can use this cocycle to construct now a line bundle over a Teichmüller space. So what is the line that I'm going to be interested in? So I look at the functions of all the parameters, so a complex structure and a pair of pens. But now if I fix the pair of pens, I only look at, so if I fix a complex structure, I look at functions that depend exactly in this way with respect to the choice of pairs of pens. And this, because this is a cocycle, this defines a line bundle on my Teichmüller space. So yeah, this is a complex line. And when you look at all the lines as you vary the complex structure, you get a line bundle over a Teichmüller space, which depends now just on your choice of sigma and the pair of the topological pair of pens. And so, yeah, just by definition, the conformal blocks that I just introduced, they satisfy this property, so they are going to be sections of this line bundle.
Who's this gamma xi1, xi2? I mean, how we define it?
Sorry?
Epsilon.
Epsilon is
epsilon.
So I first look at the infinitesimal variation of my block when I vary the pair of pens decomposition. This gives me a differential form on the space of complex structures plus pairs of pens. And I can integrate this differential form to get a cocycle.
Is there some explicit related, some formula, some?
Yeah, this guy is a sum of shortened derivatives, and it turns out that you can integrate it, and so you get a function now that is, and so now you know exactly. So I call this integral epsilon, and I get. Okay, so I have an infinitesimal variation of with respect to.
Yeah, but you have some explicit formula for this?
No, for the epsilon, no. So the real part is known. Yeah, it's some Liouville action. The imaginary part is we don't have a closed formula for it.
Okay. So it says that Liouville action has some.
Nothing to disagree.
But you take two curves which are homotopic, you take a family of them and you integrate the Schwarzian.
Yeah, but this is not explicit.
Yeah, this is
it's quite
the question is what is the result of the integration?
It's explicit. Schwarzian of.
So the real part is some, you can write it as some Liouville action of two metrics with respect to. So yeah, because basically when you fix a fence decomposition, there is a canonical choice of metric that makes the curve geodesic, and you can express the real part as a Liouville action with respect to the two. Okay.
But do you know it is non-trivial as a cocycle?
Well, I mean, so here we're working on Teichmüller space, so it's contractible.
The curvature of the bundle is by Peterson. You should define the bundle with this cocycle.
I mean, yes. So I told you that. So I told you that it's holomorphic, but I didn't tell you how to put a metric. If you choose, say, the hyperbolic metric on your surface, then it's going to induce a metric in this line bundle. And the curvature. So with this choice of metric, the curvature is on the spot by Peterson. Exactly. So not just in cohomology.
It's not just on technical. There is also action of the mapping class group.
Yes.
Say it's on the contractible space, yes, but there's also action of the mapping class.
Yes, but this is what Rémi will say at the end of the talk. I think he might mention this. No. Yeah. So exactly. Okay. So you should have an action of the mapping class group, which gives you these fusion transformations of the mapping blocks. This is not in full generality yet. Okay, so now we can apply this to some specific cases. So instead of choosing arbitrary curves and deformations, we are going to use some specific choice of coordinates, which is the plumbing coordinates. So if I cut my surface along these curves, I can deform the complex structure by just gluing some straight annulus and with a twist possibly. And these define local analytic coordinates on the space of my surface. And now I can apply this construction to this choice of coordinates. And my blocks are going to be now local in this chart. My conformal blocks are going to be holomorphic functions. And I can do this gluing of these amplitudes of pairs of pants. And I get some formulas. And so I haven't really talked about marked points, but you can add marked points if you want. But let's say we're in the specific case of two pairs of pants. You're going to this function is going to be my trace along the graph, evaluated, but the norm square with respect to this choice of metric of this conformal block. And again, so this is the block that I just defined, and this row is a product of structure constants. Okay, so I think this might be a bit repeating what I just said. Yes, okay. And yeah, actually, I think I'm more or less done. So I will hand it over to Rémi. Where's Rémi? So yeah, Rémi will. So unless there are questions, Rémi will tell you some things about CFT with boundary. Yes. C'est pas les slides
Non.
C'est quoi?
In the view, yeah.
Okay, so yes, so Sylvain asked about the case of a Liouville amplitude with a boundary. So it will be just an informal introduction to the talk that Bao Jun will give on Friday. But since it rises on similar ideas, I will just explain how to adapt by hand. Okay, so now the setup is that you have a surface with a boundary, and you have to be careful because you can be confused. Now, from scratch, you want to compute the partition function of the Liouville theory, say, on a surface like this. But so for the fields that you want to integrate in the path integration, you may have you have a further term corresponding to what you expect in the action. So this term is well, you have the boundary term is here. You have the geodesic curvature along the boundary components, and then you have another potential cosmological constant. This is a real parameter. Let's call it mu b for boundary. And you have also the exponential of the field that you integrate along this boundary component. So the field here, phi, is allowed to fluctuate along the boundary component. It's different from the amplitudes we had in the previous slides, where you had a condition.
So the integral is on the boundary of sigma.
Yes, here this is a mistake. This is a partial sigma. Some pen I can write on the blackboard. Okay, so the correlation function are of the same type. This V alpha are the exponential of the fields, except that eventually now the points can lie on the boundary. Okay, you may have some points in the bulk, some points in the boundary. You may have points here.
That's a very specific choice of boundary condition somehow. Imagine that one could say a lot about what are the possible conformal boundary conditions that you could impose on your field. Here you say the field is just free to take any values.
The field is free to take any values.
Or was it what you just said?
The field can take any values, but then when you integrate, this path integral will tell you which measure you integrate over.
But maybe you could want maybe essentially the field to be fixed at the boundary or along the boundary.
Here, the field is completely free to fluctuate in the boundary.
But you have a condition on the normal derivative.
So what's your assumptions about geometry? So you have boundary. You don't say it's geodesic boundary, it's just boundary. And when you say point, is it really a point, or maybe there's something like tangent vector at this point? Some kind of data?
I'm not sure I understand the question.
You put in some boundary condition. The question is on which parameters this boundary condition depends.
Where do you see a boundary condition here?
Huh?
Where do you
Second integral.
It's not a boundary condition. It's
a second term in the Lagrangian.
Yes. So this one. Which term in the Lagrangian is all of this? So I guess this is something around here. So you have this one and this one.
Yes.
Okay. So this is the geodesic curvature, whatever it is.
So the boundaries should yes. I'm just asking what's the structure of the boundary of your surface, which you need to write this down.
So you have a surface with a Riemannian metric on it. You have a Riemannian metric on it, G. It gives you a G in the bulk.
Yeah, sure.
The curvature. So what is the problem with my kg?
When you write this quantity, you are not assuming that you put on the boundary some extra data which you will not see on this picture.
I'm not assuming any.
You're not assuming. You answered the question. Okay.
I guess one way of phrasing this question is to ask what are the classical solutions of this particular action.
Yes.
The classical solution it should be the classical solution. So the critical points, they are metrics with uniformized curvature, prescribed, uniformized curvature and inside the bulk, and on the boundary, it's you prescribe the constant geodesic curvature.
Boundaries are geodesic.
Yes, the uniformized curvature in the bulk and on the boundary.
The boundary is geodesic, you say in class concept?
Uniformized.
No, the boundary. Basically, you ask for like a solution for you want to find a conformal metric.
Well, it's in kg.
The scalar curvature inside is minus mu or something this. On boundary, the geodesic curvature is minus mu b. Okay.
So this special, what happens in those special points?
The punctures?
No, on the boundary.
So you have the conical thing. Okay, for the special points here.
You have this picture and you have orange and
okay. So if you have if you want to look at the critical points,
yes,
you have to plug these guys here.
Yes.
Okay, at those guys. So basically, you prescribe the curvature outside of the marked points.
Yes.
And on the marked points, inside the bulk, you have a conical singularities.
Sure.
And here, I don't know the name, but it should be conical.
The question is it a cusp with zero angle?
No, it's not a cusp. It's a conical singularity. And the angle alpha, the angles are given by the alphas.
Okay.
You can consider cusp as well, but you have to take the alpha all the way.
So you say that this alpha measures somehow the angle of this conical singularity.
Phi, is it smooth? Smooth holomorphic? Phi, capital Phi.
The phi here?
Yeah.
No, it's not smooth. In general, well, here it's a formal description, right? If you want to, it's a path integral. It's a.
No, in classical setting.
In classical setting, yes, the phi is smooth, yes.
Except at the point.
Not at the points. At the points you have a singularity.
Is it holomorphic?
The field, classically, the field looks like.
The field takes value in R.
Yes, the space of maps, yes, phi is defined on the surface and real value, yes. Questions?
So I guess what I'm most worried about is that model studies, maybe not in Liouville theory, but more like in free field theories, show that in certain cases boundary conditions can be conformally invariant, and in other cases they are not. So for example, Dirichlet or Neumann boundary conditions on a free field would be conformally invariant, but in some cases, if you impose, for example, some crazy choices of gradient, you can get strange phenomena like the Arctic Circle phenomenon that will sort of preclude part of your surface from really seeing the conformal field theory. So I felt that maybe at some point you would need to say something more.
Here, everything will be conformal.
Yes.
But if you want some strange setup, I think that can give you some examples for Causal theorem. You can practice on conditions and something like that. These are the symmetries. And
Baptiste will speak about this.
Actually, tomorrow I'm going to talk about this classical problem of the boundary Liouville.
So the claim is you can somehow evacuate this discussion at this stage and just say, okay, there's some setup and...
Let's do that. Okay.
Yeah, okay.
Can ask again after the lecture. Please.
Okay. Well, so... Okay, so the message here is that you can construct this amplitude probabilistically, and so I guess you regarding your question, you may ask for the definition, but I didn't plan to explain so much. The philosophy is the same as in my first talk, instead of taking the GFF on closed surfaces, you will take. The construction is based on the GFF with. Well, you have to take any GFF that can fluctuate along the boundary. So the most natural one is the GFF with free boundary conditions, and then you plug this GFF inside and see if you can get an expression for this using this GFF. Okay, you can do so, but you can do more than this. The thing is that you also want to implement the Segal philosophy to this type of surfaces. So in my pictures, the green boundaries will be those boundaries where you want the field to fluctuate. Okay. The thing is that for the same reason as you wanted to cut your surfaces in my talk and in the talk by Guillaume, you want to do so as well to decompose such surfaces into building blocks. Okay. So in the case of closed surfaces, the building blocks were pair of pans. And actually, when I say pair of pans, I consider a mark point as the end of the pan. Okay, so in the closed case means that the surface was closed. You had three types of building blocks, if you want. So you had the disk with 2 points, the pant. So the pant was this type of things. And you have also the annulus with 1 mark point. Right. Okay, so what are the building blocks in this case? So you want to perform some cuts. The building blocks for the open case. Well, it will be, basically it will be all the configuration that you may take where the Schottky double along the green boundary component will be of this type. So let me, so you will have to perform some cuts. Let me try first an example. So here you will have to perform bulk cuts like this. Here I have to cut around here so that I have a pair of pans here. Here I have an annulus like this. And then here, when I plug the spectral decomposition here, I will end up with the building, well, this part here, I will end up with trying to decompose this type of things where I have so this is the green boundary component. Sorry, the points are on the boundary. Let me write. Okay, it will be complicated if you to understand it this way. I will have to perform cuts here that are half cuts, say, like this one. Okay. Why this one? One way to understand what will happen here is that when you have a surface like this, you have a green boundary component with 2 mark points. Eventually a mark point here. What I will do first is to try to write the Schottky double. Okay? I just double my surface identically. Okay. This is the same surface that I just and then I just take a pan decomposition on this double surface, and I will just look at the trace of my cuts on the white surface. Okay, so let me do this type of things.
And if you want your cuts to be symmetric, no?
Yes, yes, but on my picture it will be everything is symmetric. Yeah. So here I can make this cut in a symmetric way to get this picture. And then I reproduce everything symmetrically. Okay? Okay, so in the double, you would choose these cuts. And so what you do now is just that you erase what you choose, and you just look at the trace of the cuts on this white surface. Okay? This is the type of cuts you want to consider. So the difference with what we had before, so this type of cuts we explain how to do them and cut them. The difference is, now is that you may have on your the white surface, you may have this type of cuts that start with an angle pi over 2 from the boundary and come back to the boundary at some other place, right? Is that okay?
Can you draw it?
What?
Can you draw it?
I can. So you have these cuts, this cut. And of course you have the other cuts that I eventually don't reproduce. Okay, the bulk cuts, I don't reproduce them, but here you see that among all the traces of my cuts, I have this one which is specific. It starts from the green boundary and comes back to the green boundary at some other place. Okay, so you have to implement this type of cuts, and I want in my picture to differentiate the green boundary components from the orange on the blackboard, because the orange will correspond to a cut and the green will correspond to parts where the field can fluctuate. Okay? So if you want to implement Segal, you have to define this type of thing. Okay? If you look at this surface and you cut along this orange curve, you will have two parts. You will have a first part that looks like this. This part here. With 2 points. It's a half disk, say. And then you have the other component, which is so you need to have some amplitudes of this type, or of this type. The green parts here are those parts where the field is allowed to fluctuate, and then the orange cuts here are blue or red here, depending on whether you have a positive or negative orientation. Okay. Okay, so you want to define this type of amplitude in the case of Segal with a boundary, and you can do that as well. But so the construction here, the probabilistic construction, it involves the GFF with mixed boundary condition. So mixed Y, mixed means that you have some parts of the boundary where the field can fluctuate, some parts of the boundary where you have prescribed boundary conditions of Dirichlet type. The Dirichlet type boundary conditions are along the red or blue curves, and on the red part, on the green part, the field is allowed to fluctuate. You can do that with the GFF.
So what do you mean fluctuate is Neumann condition?
You take any GFF that fluctuates on the boundary, and then you plug the path integral, and it gives you something. Of course, if you change the GFF, you change the probabilistic interpretation, but the outcome is the same in all cases. So concretely, what we do is we take the mixed boundary condition GFF. Okay, so and you can see you can prove that the Segal axioms are still valid in this context. Meaning, in this case, for instance, so if you attach an amplitude that's the same flavor as I told you 2 days ago, if you attach an amplitude to this surface, an amplitude to this guy, when you glue the surfaces so as to get this surface, but then you get the amplitude composed in a nice way. So you see on this picture that there are, okay, my picture is not so good because I have only, no, it's good, I have 2 types of cuts. So here it's, you have 2 types of cuts here. You have circular cuts and what we call half cuts, because they are just like a half circle. Okay? So in this picture you will have 2 types of Hilbert spaces. One Hilbert space attached to the bulk cuts, to the circular cuts, and one different Hilbert space attached to the half cuts. Okay?
And so those half cuts, you impose that they do not encircle bulk insertions or cycles or holes in the bulk part of your surface. So the orange curve here, for example, it cannot encircle an operator insertion in the bulk.
Yes,
for example.
I can, then here I will have if I cut here, I will have insertion of operator in the bulk.
On the right hand side, could the orange curve surround the cross that's in the bulk?
Disk with one puncture.
It should be, yeah.
You need to
inside puncture in the boundary disk.
In the boundary disk thing.
Here, yes.
Yes.
I think he's asking if there can be an inside singularity.
If I can have an insertion inside,
yeah.
Yes, I can.
Also, the orange curve, can it ensure the hole in the surface? So if you look at the upper
orange curve.
Not.
So there's a hole in this surface.
This one?
Yes. Can the orange curve turn?
Yes. Okay, so you want to do this,
So
right?
around the boundary touching orange curve.
Du coup, il y a du bord au bord qui entoure le trou.
Yes. This type of. Yes, you can. This is what I more or less. No, it's not. Okay. It's not exactly, but I could have just put a hole here instead of this green. Okay.
Sorry, why you can't have a small disk around one cross?
Why can I have a small disk around one cross?
Yes, just little circle surrounding the white cross, white X on your surface.
A little cut surrounding.
Yeah, like this.
I can.
You can?
I can.
But you don't have it in the list.
Okay, I didn't. Okay, so there are. Okay.
But this is
Different
already what
questions.
I presented, I think.
I think we are not okay. Perhaps I can summarize. The cuts, you can do whatever you want as a bulk cut, which is just a loop, or as a boundary cut that starts from the boundary with an angle pi over 2 and come back pi over.
As long as they don't cross.
Of course, as long as the cut don't cross. So you can do everything as long as the cut don't cross. That's one part of the series of questions. I think I can keep on. But I can keep on drawing all the pictures you want. You can take any cuts, as long as they are analytic. Then there's different story, which is what are the building blocks, and I didn't finish. And so the building blocks, so my initial goal on this picture was to draw a series of cuts that decompose my surface into building blocks. I said the relevant ones are to let them you double the surface, trace the cuts corresponding to a band decomposition in this sense, and then you see the trace on this surface. And now I'm going to draw them. So of course you have all the closed case that are still living in this setup. So all these guys can appear. So you have the annuli here, for instance, and the band here. But I could have also done a circle with two crosses inside, and that would have given me this one. So all these configurations are still possible. But then you have some further possibilities here. Actually, you have this type of things. And two cross. Let me keep on keep on the colors for the stuff. So here you have 1/2 disk and 2 points on the boundary. You may have as well a boundary. This one. I will just write a disk with 3 points on the boundary. And I have also the configuration with one point inside and 1 point on the boundary.
Can you comment on the left picture where you have orange arc? You have three basic pictures, triangle inside, and then on the right and on the left you have orange, You have semi-disc with orange top and green bottom and 2 crosses.
Which
under the word open case, if you go,
well, let's show.
I'm talking about this.
This one?
Yes.
Comment on this one?
Yes, so what exactly is going on here?
What exactly is going on?
Why orange differs than green?
What's the difference? So here, when you have cut this part, you see that the field, when you define this amplitude, there is a path integral. Okay, so the field you are integrating over, on this component here, it will have a prescribed value. Because when you cut, it's a conditioning, probabilistically, it's conditioning, so you will prescribe the value here, and when you glue, you will integrate along these boundary values, okay? The green part here means that the field can fluctuate here. So it's free, and the boundary term is of the same flavor as I showed you. So here there is no directed condition, just that you have.
Rémi, do you have something like the annulus where you have one point on the boundary, such that the double is the first one on the list above?
You have an annulus, yes. So yes, okay. So
this one where you open the.
Yes, you're right. I forgot something. So no, you're completely right. You may also have this. So
there are 6 cases.
Yeah, actually there are more cases. So you have also what you said is this one. Because all the configuration where instead of a cross I can have a circle. So did I forget?
So maybe above you should also have the sphere with 3.
You can also have this. Yes, sorry. Yes, you're right. So you can have also the annulus, but instead of cross you can have a. What is
it's half point or something.
There's no insertion?
The half point, yes, the half point. Okay, let's write the half point. Well, what I should do is that I should take all the configuration that when I double along the green boundary condition, I will cover all the possible cases here, and I should be exhaustive in my. So if you double this one, for instance, if you double this one along the green boundary, you get the point. Okay. If you double this one along the green boundary, you get this guy, and so on. That's okay.
You comment on the right lower one. Yeah.
This one.
There's no puncture inside.
Yeah. Okay. You're right. Okay. If I double, so if I double this guy, what do I have? I have an annulus.
Get a point.
Get a point. This guy is. I'm trying to. Yeah. It's a point. Okay.
No, the green goes around. No? Bottom green is wrong. It should go around.
It's just a different color.
Okay. I choose the other.
And is there some viewing rules of whom you can view to whom? You
Okay.
have some elementary pictures, and now you're saying
Yeah, okay, so-
picture by viewing them. So what is the viewing rule? Whom you can view to whom? On the right.
Okay, perhaps here. You can glue. Okay, so when you represent your cuts locally, so half cuts have to be glued to half cuts.
I know you have 2 different colors, so who are?
For the green, you don't do.
Yeah. He has to see.
So the cuts, there are half cuts and full cuts. See.
I mean, you have 2 colors, orange and green. Do you understand correctly that you can glue along one color but not along the other?
So in my pictures here, you can glue only orange with orange.
Yes.
But there are 2 orange, the red and the blue, corresponding to orientation.
Sure, you have oriented orange.
Yes. So in my picture, it's not orange, but I should color either in blue or in red this orange colors, and I can glue orange red with orange blue. Okay. And of course, half with half and full with full.
No, but you also have green.
Green, they cannot be glued together.
Is green like a physical boundary? You can do the Schottky double.
Yeah, the green is only used to figure out what is the Schottky double.
I don't know what means figure out. So you have rules. You have surface which has oriented green and oriented orange and green. And the rule is that you never glue along the green,
Yes.
and you glue orange with reverse, so that reverse orientations match. That's the gluing rule. That's
the gluing rule.
What about the crosses?
The crosses, they don't glue, they stay.
They stay because they stay on green. So the crosses only on green. There are no crosses on orange.
Yes, they stay because they are on the green, there is no crosses on orange.
I just wanted you to somehow to say these rules to us in explicit form.
Yes, but I was planning to do it slowly so that we can discuss. And I was expecting your questions so that you make me say the rule one by one, slowly. But you did your job.
One more question. So the angle between green and orange, is it right angle?
Right angle. Yes. Okay. Probabilistically, you could also modify the angle and pose some figures like this. So you could have on the half plane instead of the disk, you could have a cut like this, okay, with an angle which is different. Of course, you can glue as long as the angle matches to pi. But we have to fix the rules. So for now, so we skip this situation where we start.
But we didn't prove the Segal if it's not half.
Yeah, but
it's more complicated.
Yeah, but it works.
Maybe it works.
No, there's no problem.
No, there's determinant gluing and it's a mess.
Yeah, but it works. You can do that. We see no point in doing this. We have to fix the framework. Okay. For now, we don't see the use of doing this.
But angles matter.
Angles matter, yes. Because then, when you glue, there are some Goni type conditions. You have to match the angles. There are technicalities. But in spirit, at least in spirit, you could do that. That we haven't seen the use of this for now.
Can I ask one last question? So in the closed case, you don't have this sphere with 3 punctures.
Okay. As a building, when you cut a surface, you won't get a sphere at any time with 3 punctures. Okay.
Yeah, but in this picture, then the 3 cases, there's no sphere with 3 punctures.
The only way you can get the sphere with 3 punctures is when you start from the sphere with 3 punctures.
Okay, good. But if you double the green, so if you double the one above, yes, you get.
Yes.
You get the 3 sphere with 3 punctures. Yes. Okay, good.
Okay. If you start from this picture, yeah. But if you start from this picture, you have this picture from scratch. Okay. But as long as you cut a more complicated surface, you cannot end up like this. But in philosophy, well, now these are the building blocks, and in the same way as Guillaume told you, now here we will plug something to. This will be seen as amplitude. So it's an operator acting on the Hilbert space to the power 3 Hilbert space attached to the half cuts. So you will have to plug.
Which polar? You should tell us always which polar cuts.
So this is an amplitude. It's an operator. This guy, the amplitude, acts on some Hilbert space. I put a plus to say that it corresponds to the half cuts. To the power 3.
Okay, so orange.
Orange. And so you will plug some states here. When you plug the primary states corresponding to this guy here, the question, you will end up computing this guy here, for which you have a dose-like formula. And so this was, I had to finish my talk, but basically in the end, you have to compute, when you fill all the holes here, so with the primaries attached to the bulk or primaries attached to the boundary cuts, you will end up with this type of structure constants, which corresponds to the Riemann sphere with 3 points in the bulk. Here, this one is a bit specific. It's a degenerate one that does not come from my picture there. And this structure constants, they admit those like formula that Jean computed, and I'm not sure you will give a talk about that today.
I will talk about it.
I will talk about that, fantastic. And okay, so just to finish, I would say, so there are probabilistic proof of this fantastic formula that physicists derived long ago. Well, just the outcome is that that's not the right side. Okay, you have a bootstrap formula for these surfaces. It's just that, let me just write the bootstrap formula. In the end of the day, what we have, you have a product of structure constant. When you compute the correlation function of this surface, you have a product of structure constant times the block, the conformal block. But the difference of Guillaume, you don't have the square modulus of the blocks, you just have the block. Well, okay, there is a parameter here, r to the plus to some power. What are these blocks? These blocks are the blocks of the Schottky double. Okay, so you take your surface from scratch. Here, there is only green. You double along the green. You have a closed surface. Guillaume explained more or less how to define the block. They are here. And you integrate. The philosophy, so what you need to implement this is just another spectral or Plancherel formula associated to the Hilbert space corresponding to the half cuts. And for this, you need two diagonals and Hamiltonian. And the Hamiltonian, in that case, is just the Hamiltonian that you get when you glue together half alumni with these colors. You get a semi-group, and its Hamiltonian can be diagonalized. Okay, it was a very short story, and you may have more explanation on Friday with Baverez. Thank you.